1 minute then?
Yes, we will finish earlier.
Okay, so we're ready to start today's session. So it's my great pleasure to present the first plenary speaker for today. So it's Professor Tassos Bundis from University of Patras and Yaroslavl State University. So today he will be talking about a pedagogical approach to limit cycles. So Mr. Bundis, you can please start.
Начинаем. Говорим по-русски, а?
Можно по-гречески даже.
Спасибо, Сотирис, за приглашение на столь хорошо организованную встречу. С черченными приветом, уважаемые коллеги, хотел бы я быть с тобой в эти дни, and I would like to continue my whole lecture in Russian. But Sotiris was very strict. He told me, no, I have to speak in English, so I'm afraid I will not give the rest of my talk in Russian. One day I will do that when I'm with you. Well, I decided to do something which is not really for a conference, but more for the older scientists, but more for the younger ones. And because the center, as you know, of integrable systems in Yaroslavl is focusing on integrable systems, and my purpose also when I visit you is to introduce nonlinear dynamics and non-integrable behavior and bifurcations and all that. So I would like to say something that I have collected from my experience and should be quite useful to younger members in the audience who would like to see this business of limit cycles in a unified perspective, somehow gathered together. In various aspects of it, usually the books will focus on one particular aspect like Hopf bifurcation and the theory of Hopf bifurcation. But well, in 2 dimensions, I would like today to say something about more than 2 dimensions also. And at the end, surprise you a little bit with some occurrences of limit cycles that you may not expect in realistic systems. So let me begin from a very pedagogical and well-known system in 2 dimensions of 2 species of the big fish and the small fish, and how they eat each other and feed from each other and survive in an environment where, under these 2 equations, they can perform periodic oscillations. Or that's all we see. There is nothing but periodic oscillations on the first quadrant. Now, that's not very interesting, but it does show the cyclic behavior nature, and there is a stable equilibrium point. So immediately the student realizes that the focus of attention should be around fixed points. Later on, one can find manifolds, one can look at more global structures, but the properties of fixed points are the first place to start. Okay, well, it's surprising though, why should they have all these circles around the fixed point, and what can this be a limit cycle? Of course not, there's nothing limiting here. Anyway, there are many cycles going on around. So let's think about this. How do we go about it? Well, we do know that we must look for these fixed points in general, right? And that's what we do with the Lotka-Volterra system, everything. We find them by solving these equations. And then you see this is the process of linearization. So what do you do with fixed points is you focus very, very close to them. And this can be tricky. This can be a little dangerous sometimes. But it is very, very useful, many times, very informative. So you proceed on with your usual knowledge of calculus and Jacobian matrices, and you try to determine all the eigenvalues of the linear system, and then you find out they are complex in general. But then complex in general means that if the real part of lambda is negative, then the exponential solutions, e to the lambda k t, will all be attracted by the fixed point. It's unstable. If all the ak are positive, then the exponential behavior will tend to send you away from the fixed point. So you say, it's an unstable, repelling node. But then some of the ak are negative and some of the ak are positive, so you say the fixed point is a saddle, has a n-dimensional manifold approaching the fixed point, another dimensional manifold going away from the fixed point. So everything is clear. And that's not what happens to the Lotka-Volterra system. Because what about if some ak are zero? Then what can you say about the dynamics in phase space? Locally, I mean close to the fixed point. No, as the older professors know very well, all this local analysis is not sufficient to determine the stability, even in the neighborhood of the fixed point. So now let's go back to Lotka-Volterra. There's two fixed points. One is at the origin, it's unstable. The other one is a stable one. Why? Because elliptically stable, there are all these closed orbits around it. And the point is that the eigenvalues at this central point are imaginary. So this is the previous case of ak being zero. What can you say about it? Nothing. You can say nothing about it globally. This is the case where you don't know what happens. It predicts circles, but you have missed higher order terms, so you don't know what happens. Well, in the case of the Lotka-Volterra, we know there exists an integral. Then if you know an integral, you're saved, because when you add the two equations, you get this result. And then when you multiply by a b, divide by x1, do a simple manipulation, then you arrive at equation 5. And what you see in equation 5 is exactly the family of closed curves we saw in figure 1. So the mystery is solved. But unfortunately, for all those friends who love integrable systems are very, very rare. And so life in general is not integrable. And what may happen to the big fish, for example, is they may start to die. The second equation shows a term that you may model as the deaths of the big fish with an epsilon y square. So now you say, I suppose I introduce such a term. How would that change the behavior near the fixed point? Well, you know what might happen? Well, first of all, let's see what the eigenvalues are. The eigenvalues now are of this form. So you see, no matter how small epsilon is, it's a positive number now. The fixed point becomes a sink. And what happens, if you wanted to, for some reason, you wanted to make epsilon negative, then it will also become an unstable node. So mystery is solved in this case, where we don't have an integral, but we know what happens. Well, if mystery is solved locally near that point. But what happens more globally? What else can happen when epsilon is introduced? Can something come out of the fixed point some other kind of bifurcation? And the answer is yes. We could have a limit cycle appear. And that is what happens after the so-called Hopf bifurcation. Limit cycle must be a very interesting thing because it's an isolated periodic orbit, right? The family of infinite family of continuous parameter closed orbits belongs to integrable systems. We said these are rare. Excuse me. Usually, we do see a single limit cycle, one periodic solution which nature prefers, for example. So that should be very interesting, and we have to find out what happened. Well, there is a case, for instance, out of the origin in the middle here, this could have happened. Well, okay, it could happen. How it could happen? Well, because mu crosses the value 0, yes. So from the orbits going inside for mu negative, now the orbits are going outside for mu positive, and maybe there could be a limit curve on which they could go, but that's not always the case. This is only a necessary condition. There is a sufficient condition. If we do have a Hopf bifurcation and we are going to see a limit cycle, however close to the point, it will be born. To do this, we must first change coordinates and go to normal forms. So here's the theory starts and says that, well, if you want to decide, you first must write your system around the fixed point. So move from x1, x2, move around the fixed point, place yourself there, and write the system in normal form. And normal form means that in these coordinates now about the fixed point, there is a linear part which is in normal form as far as eigenvalues are concerned. But the whole system then has changed coordinates to normal form, following the leader, who is the linear terms. The linear terms tell us what to do. So we make the transformations multiplied by the matrices and arrive nicely at this. I'll show you some exercises, and the students can do it when you get my talk online recorded, then you are able to follow it. Okay, so you do this, and then the theory says, and I have a bibliography at the end of the talk, you will find very nice books about this, that amazingly there is a quantity called A. And if you take your F and your G all in 2 dimensions, and you have triple partial derivatives, this is triple partial derivative with U, triple partial derivatives, then double partial derivatives, then all of that, and you evaluate it at U equal to 0. If this is different from 0, then you know you're going to have a limit cycle. So that's a very common occurrence. Some quantities are all the time different from 0. It's very special to be 0. So if you're not equal to 0, then you'll find a limit cycle. So it's a very, very common occurrence. And we can tell you from perturbation theory what the radius of the limit cycle will be to this approximation, to lowest order approximation. It's going to be minus mu over A. So now, if your A that you found from 9, equation 9, is positive, then you have a limit cycle appearing for mu negative, and it will be unstable. You can think about the detail, it's very easy. But I'm telling you, we know the answer. While if your A happens to be negative, the limit cycle will appear for mu positive and will be stable. What did I say? For A positive, we have limit cycle for mu negative and this unstable, and for A, okay. So there we go. We have a theorem and we can use it. So let's take an example that we have a dynamical system. It has a fixed point at 1, 1, and I want to find out if there is a limit cycle appearing after a suitable perturbation. So somewhere in the equation, I have to introduce a small parameter mu. What is this parameter mu? You remember it is the real part of the eigenvalue near the fixed point. So we know what this mu must be. So here we are. I have rewritten this. The coordinates xi and eta, I placed 1, 1 in the center of my attention. That's my fixed point. I introduced this small perturbation that I said mu in the real part, in the eigenvalues. Well, you see this in the next equation below. Here it is. Okay. So I have introduced it here. So then when you write this in normal forms, it leads you to these equations. So now you have your mu as the real part of your eigenvalue. You have your dynamics perturbed by this mu. The eigenvalues are these, fine. And now you say, let me use formula 9. So when I say formula 9, you remember it's the big one with the many derivatives, partial derivatives. This important formula that we have to study this. So now you calculate it, very easy. F and G are polynomials, etc. And at the fixed point, the number is a equals minus 1 over 9. So that proves that there is an unstable limit cycle that appears for mu positive. And you can estimate its radius also. All right. Now, excuse me, I have some exercises along the way. And the students will have some fun to try to solve them. They're easy. And now you may go back to your favorite Lotka-Volterra and you say, hey, what happened when I changed the epsilon? Introduce that epsilon. Nothing happens. And there is no limit cycle coming out. This is an exceptional case with this particular equation that I used, the perturbation. But then, when I did the calculations with the Hopf parameter A, I couldn't find A because the terms F, G, etc. contain, the equation you saw before contains terms of 1 over epsilon. So it doesn't make any sense in perturbation theory if you want epsilon to be small and to have a bifurcation at epsilon, you obtain terms 1 over epsilon that go to infinity, for epsilon go to 0. So I cannot use the theory, and that strongly means to me that I cannot, it doesn't exist. If it did exist, I should find a very finite result. But you cannot do it by the theory, and then you realize that when you search and look for it numerically, whatever, it doesn't exist. So finding limit cycles is not a very trivial thing. It's interesting, but they occur very often, but certainly it's not such an easy subject. You have to think about it a little bit. Many things can happen. Now let me take another example, again, as an exercise for the student. I put the mu here. Now it's just like the real part of the eigenvalue. As I said, I have a small parameter, I have a system. I can prove that 9 yields A equals minus 1 over 8. So there is a stable limit cycle when mu is positive. Now notice something interesting that will happen as mu grows. As I increase mu, my limit cycle becomes bigger and bigger. And then all of a sudden, for mu greater than 0.07, the limit cycle disappears. What happened? So you have to look at it carefully now. I'll show you to you the answer numerically. And the only thing you could have done, actually, is go to look for another fixed point. Here's the picture for mu 0.05. You see the green orbits from around. This is the velocity field. They go around and they finally converge to a limit cycle here. If you start from beside the origin, orbits go out, and converge to a limit cycle. No problem. But then you go to mu equals 0.07, it doesn't work. The green orbit here, or trajectory, moves around as it should, but then instead of embracing a limit cycle, it goes away. The blue orbit goes out, but it doesn't find a limit cycle, and finally it also goes away. What happened? Well, I guess you must have noticed it already. There is another fellow in this story, another actor in this drama. And if you don't know him, is another fixed point. So we should be careful about where our fixed points are, because this other fixed point is a saddle and goes on and collides with the limit cycle. So the limit cycle is destroyed for mu 0.07. So that's a more global phenomenon. Beyond the theory, we found the limit cycle, but when the limit cycle goes out, there can be some interesting collision effects like this, and you must be aware of those when you study. All right, well, that was interesting, but now let's go to some real-life models. It's a model, it's a very simple model, yes, but it does represent something that in chemistry people call autocatalysis. They are certain reactions which themselves are autocatalytic. What does it mean? Well, you have in this famous Brasilator model some quantities that are available in unlimited supply. And what's the property of autocatalysis? You see, you produce the product Y from X, but then at another step, Y joins X to produce X again. So there is a cyclic phenomenon in these equations which gives you the idea that maybe there is some limit cycle, a periodicity in this phenomenon. Now, chemists and dynamical chemists know very well how to write differential equations which describe the evolution of the concentrations of the substances. So the concentration of X, for example, capital X is little x of t, capital Y is little y of t, and the others are constants, A and B are constants. So let's look at this simple example again. What happens? Well, nonlinear dynamics can do its job because, first of all, we found there is a single fixed point. Okay, that's good. Now we are approaching the possibility of periodicity about the fixed point. What are the eigenvalues? Here they are. Okay, now what are we interested in? When is this guy becoming zero? This is the point, because they become complex when this quantity, first of all, I make another observation here, yes. Look at the quantity under the square root. These become complex when this occurs, okay? And in fact, the fixed point becomes an exact center, you see. Why? When a square is equal to b minus 1, then this quantity becomes 0. And this guy should be imaginary. So we have circles, orbits rotate around it. I'll show you the other eigenvalue too. I times omega. There is this imaginary quantity. This is 0. So, okay, so this is the case mu equal to 0 we were discussing before. So let's go to this case, which is an example. A equals 1 and b equals 2. You see, b equal to 2, a equal to 1 satisfies the condition of 0, real part. Okay, so then that's the one we have mu equal to 0. So now we can even apply our theory to this point. And here is our expressions written around the fixed point. So you see your linear part, which has the eigenvalues I showed you. You see the nonlinear terms now. So we analyze theoretically the van der Pol oscillator. And then we find that, well, yes, we must make a transformation. We multiply by p by p minus 1. And we have now what we wanted to find. You see the normal form of the linear part. Mu is 0. That's why these are 0. We are in the territory where the theory of result number 1 is going to work. So now we calculate partial derivatives. We use our theoretical result and we find a equals minus 5 over 8. So this means we get a stable limit cycle for b greater than 2. That is the theoretical prediction. Okay, now let's go in the next page to verify that this is true. We take b equal to 3 first, I guess. Yeah, when we see the presence of the limit cycle. But then we take b equal less than 2, and then the limit cycle does not exist. Let's look at it. Okay, on top, I have set a equal to 1, b equal to 3, and then that verifies that the limit cycle exists. You see the oscillations on the left of the two chemicals, and you see the limit cycle on the right. Fairly big one, huh? A really big limit cycle. Stays there for a long time. However, when b is less than 2, then the limit cycle does not exist. And this is when we have a focal point. Okay? So b equal to 2 is a critical case. We know this theoretically. Now we verify numerically. We find the size of the limit cycle of this phenomenon in this very, very, very famous Bruselator model. Very important for excitable systems and other things. I'll tell you more applications later. Okay, that's the Bruselator, but then people ask, are there limit cycles in many dimensions? I mean, we have been concentrating a lot to 2 dimensions, and the theory of the Hopf bifurcation is in its simplest form 2-dimensional, because 3-dimensional will introduce new eigenvalues, and you have to be careful. Bring in normal forms, study the normal forms very carefully. When you go from 2 to 3 dimensions, the problems are quite serious. Okay, you know that the Poincaré-Bendixson theory applies only to 2 dimensions. See, and that's very difficult. In other words, it's a theory Poincaré-Bendixson about limit cycles, but unfortunately it applies only to 2 dimensions. So things become quite difficult when we go to 3 dimensions. Oh, one might ask, do they exist? Well, for this reason, I picked an example from a famous paper on a Rikki-Take model, a nonlinear system. It's one of the first that was studied for strange attractors, chaotic behavior, lots of other things, representing this physical dynamo model of the Earth switching magnetic fields every so many years. And there is a very simple model, but we don't care about chaotic behavior now. We want to know about limit cycles here. And now things you'll see become a little more difficult. We have mu and a free parameters, very good. Indeed, we can verify numerically the 17 has a limit cycle. How do we do that? Well, you see, here it takes a long time. Let's start with a blue curve somewhere, now 3 dimensions. The blue curve moves this way, this goes in, here, right? Goes in, now goes out, comes in, and starts to move slowly towards some limiting cycle. But you don't know that unless you look at another initial condition, the red curve. The red curve starts from inside this limit cycle. It goes out very slowly. So I haven't followed it all the way. It takes a long time. In between the two, there is a convergence after a long time to some cyclic behavior. Not necessarily a circle, may not be a 2-dimensional object, but it is a cycle for sure. And now that I found it numerically, you may say, and I have to be a little bit more detailed, carry the integration further and further. You can go and find the limit cycle if you like, but you can ask me, how would I know it? What can I do theoretically now that I don't have this beautiful Formula 9 anymore? And so the question is, where did it come from? At least I would start from what else? Fixed points. And so let's look at a fixed point. That's a nice exercise in algebra. I mean, the students should have a lot of fun here, because you have to look at fixed point 17. It starts to be a little complicated. There are x1, x2, x3, all the fixed points, okay? x2 and x3. But then we have to study eigenvalues. And now you get into cubic equations for lambda, because we're in 3 dimensions. But fortunately, in this example, I was able to derive this cubic equation, 18, which I was very happy I could say something. I don't have to solve a cubic, it becomes very awkward. I come to this and I say, hey, lambda 1 is minus 2 mu. So at least we have a dissipative dynamics going in. Okay, well, that's very good. But what happens about the other two eigenvalues? And when the other two eigenvalues are around that point, actually 2 points, the one is x1 and the other is 1 over x1 over x2. I think it's there are two fixed points here, I think plus minus. But now the plus doesn't interest me, because plus here means your lambdas are real. So you have a positive lambda and a negative lambda, and you have a saddle point, forget it. But the minus tells you where to look. The case of the minus sign of the corresponding fixed point with a minus sign is where you should look, at the negative side, because then this becomes imaginary. And so you suspect now that a Hopf bifurcation might exist that would lead to the birth of a limit cycle. So it's a very nice exercise. I didn't finish it completely, but I'm sure a student can now finish it and study this limit cycle in more detail. What happens to it? Does it become bigger, smaller, etc., etc.? It's a very nice example. So now let's come to something that I'm sure all of you know, especially the senior guys in the audience. All Russians know dynamics. They also know nonlinear and non-integrable dynamics, as well as integrable. They know very well what a van der Pol oscillator is. And it's interesting to recall that this fellow is a very interesting guy. He was an electrical engineer back in the 20s. He was working in Philips, the well-known company. You know, he was very much in love with circuits, electrical circuits that lit a bulb, a bulb, and you wanted to make them have a feedback property and behave in a kind of oscillatory fashion. Now that was new. In electricity, you only think the current flows one way, but here we have circuits that can have a feedback property, like the Brussellator had this special autocatalytic effect. And now van der Pol's equations for this setup, the circuit, and if I drew the circuit, it's a bit complicated. I don't have the picture of the circuit, but you can find it in the books, the van der Pol circuit. It's a bit complicated, but it's described by very simple differential equations, and that is the great contribution by van der Pol, who actually believe it or not, he found in these oscillators in 1920s a little chip, something went aperiodic, and that was chaos. He didn't know it at the time, but he observed it. And so he was one of the fathers who discovered the idea of chaos, unpredictable oscillations. But he set it aside and focused on this example. Now, let's write this as the famous van der Pol equation. And you observe now, this is a two-dimensional model. It has a parameter mu, and when x of t is very large, the second term is positive. Look at this term here. It's like a dissipative term. If x squared is less than 1 in the region x squared, then this term becomes negative, minus mu. So mu is positive here to begin with. So if you put a minus before mu, this will become a unstable point at the center. In other words, motion should spiral out. But then, if it spirals out, x squared is going to become eventually bigger than 1. And so in the region bigger than 1, it's going to become positive. So then this will be like a dissipative, will bring you down. So you have a force bringing you to the origin, and a force, quote unquote, pushing you away from the origin. So what happens in between? Well, in between is this beautiful energy feedback relation that van der Pol discovered. You get a limit cycle. That does not come from a Hopf bifurcation. There is no Hopf bifurcation at this point here. For mu greater than 0, this is what you get. So when the value of mu is very small, 0.01, 0.1, 0.5, 0.1, you see you get things that look like circles, and then they look like a nice elliptic type of curves, and then they start to take a strange shape. And as mu grows, 2, 3, 4, 5, the shape of the cycle changes. So what happens? Well, it's very interesting. This is exactly what happens in real life systems like our heart. Because biological oscillators called excitable oscillators in nerves, neural current flow, there are times when you see in between the motion is very low. Your heart doesn't beat here, very little low activity, but then bump, it beats. Then low activity, and then it beats. Well, that's what happens in the figure on the left. We start with, look at the points, very slowly moving at this point and very quickly going this way. So this is a two-time problem. You need two time scales, one for the slow movement and one for the rapid movement. This in biological systems is extremely important. It's called an excitable behavior. It is in neuron biology, very classic model. So you see a limit cycle can be very useful. Okay, now I will finally tell you in the last 5 minutes or so some recent work I was involved also. I did a little bit of analysis here because my friends from Iran, I had a very nice guy, Jafari, physicist, I think. Sprott is very well known in mathematics. I think he was the advisor of Jafari. When they published in 2013, for the first time, a very large, about 15, 20 examples of three-dimensional systems without fixed point. This was a surprise, you see, because if you put, except the origin, of course, yeah. Well, no, sorry, without the origin, because A has to be different from 0, right? A has to be different from 0. So if you let A equal to different from 0, there is no fixed point here possible. So what happened to these nice things that I told you about? We cling on to fixed points and work with them, etc. Here we don't have them. And if you put y equal to 0, for example, this doesn't work. Here or here, etc., it doesn't work. So these are two just modeled. So another interesting thing they studied in some, what did they do in that publication, 2014? They found chaotic attractors for this model. This is a four-dimensional model now, equal to 0, no fixed points, but they have chaos. So what else do they have? Well, they have limit cycles, believe it or not, in 4 dimensions. They have limit cycles. And now this is difficult to find. Analytically, I'll show you some efforts I made to find them, but it's difficult to find. And what happens then that it's very nice, amazingly, in the fall 2017, these guys came in touch with me. And they told me, you know, 22 equal to 7, there is a limit cycle around the origin for some reason. Hope bifurcation, I have not studied it to see if that is the case, but there's no fixed point. If there was a fixed point here, you would say, it was a Hopf bifurcation, but there isn't. And then surprisingly enough, if you move away from this limit cycle, you find chaotic attractors. So they coexist, chaos and order coexist in this model. That was very interesting to me. And I thought that, okay, let's study it further. But now you say, these are attractors. So what is the region of attraction? How far do I go to follow the limit cycle? And it's unbelievable. The region of attraction of the limit cycle is in this picture of a monkey. You see his eyes here and this beautiful picture. All the blue, light blue points, they all go to the limit cycle. Incredible. And only the red and green points go to the two chaotic attractors. So the system likes to go to the limit cycle, in principle, in phase space. This is a projection in phase space. But it also likes to go to the chaotic attractors. Well, okay, I thought this was interesting. And one thing I could do to help these guys is to introduce them to some periodic orbit analysis, and indeed you should be able, with a simple Fourier series, to at least find where the limit cycle is, approximately. And you can do it. If you try with a few terms of the Fourier series, you try it, you substitute, you equate the cosine and sine terms, and all of a sudden you come up with some analytical formula that tells you approximately, for example, how the amplitudes behave and how the frequency of the limit cycle depends on the parameters. 10% accuracy. This is not a very serious approximation. But look, I didn't spend too much time to do it. I got this in half an hour or so, and then I stopped because I'm not interested in more accuracy for the limit cycle. If you are interested, you can do it. You can substitute, find beautiful Fourier series, and you can get a limit cycle to many. But I would like to end with this talk by telling you some other extremely important thing these guys did from Iran, and I was involved a little bit in their study, was the fact that now they decided to put such 4D systems. Imagine they were, biological kind of elements, and you put them onto a ring, and they communicate not only with the nearest neighbors, but they have long-range interactions. And this guy in this ring also interacts with 21, but not the others. So there is a long-range interaction. And now all of these limit cycles are hopping, jumping around, coupled to each other with a parameter D. The important parameter is D, because the D measures the coupling between all of these guys. They are coupled. If you set D equal to 0, they're all independent. So now let's increase D and see what is the role of the limit cycles in this much more complicated system. Increasing the parameter D, we found a very important phenomenon. I guess for the younger members of the audience, you should look it up if you haven't heard about it. It's the so-called chimera states, which are clearly seen in biological systems by now, and complicated ones. This was just a model. But you see, let's see what happens. Now, we increase D. When D is positive, here, D is very little. So there is very little coupling. So this is asynchrony. The oscillators are oscillating asynchronously. Then all of a sudden, when D becomes greater, D point 0.05, many of them begin to move on a limit cycle behavior up and down, up and down. And some of them are asynchronous. This is called a chimera state. Why chimera? Because chimera means the mixture of two opposing things. So this is synchrony, meaning limit cycle behavior. This is chimera, chaos, meaning chaotic behavior from the strange attractors. So that is it. Now, if you couple them more strongly, then the chimera has now the two parts, and there are two parts are synchronous, and then you keep on growing the D, and then you still have limit cycle behavior, but the other points also multiply, and that is interesting for some reason in this model. So there you see, when you know about limit cycles, you can study their behavior coupled to other oscillators. Okay, well, this phenomenon was predicted actually mathematically. That is interesting. First mathematically, and then it was predicted by Kuramoto and Batoktok in Landau, a very beautiful, actually, equation with an integral equation, PDEs, with an integral equation and a compact support inside the integral. So they found this behavior of localized synchronization, and Abraham and Strogatz related it to bifurcations in dynamical systems back in 2004. So now they are very, very important, and particularly the experimental observation in physics and science. However, even in chimera states where there are this chaotic behavior, there still are in our physiology, in the human body, in biological systems, a need to have an oscillation. You must have somewhere some kind of periodic oscillations that are stable. There may be chaos around, but you need to focus on what is periodic. And that's why limit cycles are very important. I hope I have convinced you this is the case. As many applications, and I want to thank you all. Spasibo na vaše vнимание.
Special, thank you very much. Okay, are there any questions or remarks? Okay, one question.
Professor Buntis, thank you very much for lovely talk. I have a really...
Dima, yes.
Yes, it's me. That expression with derivatives of third order that we had at the beginning. Is there some qualitative geometrical way to understand this expression?
That's a good question. That would have to depend on looking at the geometry of the solutions and how they try to turn around the point to form a cycle. Yeah, I am not aware of that. The fact that we are limited in 2 dimensions already is a very important geometric effect, and allow us to think about circular or motion around a point. Maybe you can do it. It's an interesting way to look at it. So instead of looking at analysis and solutions expressed in terms of this, I could look at the geometric features of the orbits. Yeah, possibly. I have not seen it this way.
Okay, I see Harris has a question.
Who's Harris?
Harris Kokos, yeah, but he has his microphone switched off. Harris, you should. Yeah.
Okay.
Hello.
So, can you hear me now?
Yes.
Yeah, we can hear you.
Έχουμε ηλεκτρικό, όλα καλά, έτσι.
So, not for long. So, I just want to ask something probably naive. You mentioned limit circles, but can we have also limit objects of higher dimensionality? Let's say limit spheres.
Yes.
For example, if you have a system with 3 degrees of freedom.
Yes.
Thanks.
Yes. Well, we certainly have attracting tori. So about spheres, I'm not sure. This might be more delicate to define what do you mean I approach a sphere geometrically also. This goes back to the question by Dima, but that's more tricky. What I know very well is that there are attracting tori. So the torus, after all, if you intersect it with a plane, say, you have a 2-dimensional object. And so if you extend this to 3 dimensions as a torus, yes, you do. So I would be very, very eager to believe, yeah, there are such. If you take your favorite Hamiltonian systems with your beautiful n-dimensional tori, and you put a little bit of dissipation, there's a lot of chance orbits will start to rotate around the tori.
Thank you.
Yeah.
Okay, any more questions or remarks?
No, I have only this, the set of, I would urge you to look at, there are many Russian references, of course, that you know better, and your professors know them better. I just concentrated on Guggenheimer Holmes here, and Stephen Strogatz is an excellent book on Nonlinear dynamics and chaos. So this is more the rest of the world. No Russian references here, unfortunately, but who can forget the works of Bogolyubov and
okay.
many others. Yeah.
Thank you very much. Okay, let's thank the speaker once again. Thanks very much. Okay, πρέπει να κάνετε stop sharing. Θα είναι ένα κόκκινο.
Να κάνω stop sharing, ναι.
Okay, Harry, καλημέρα. Okay.
Morning.
We can see you. Can you try to share your screen? Okay, so yeah, okay, we can see it. Maybe you can make it a full screen.
Yeah. Can you see that?
Yeah, that's perfect. So the next plenary speaker for today is Harris Kokos from University of Cape Town. and he will be talking about numerical investigation of spatio-temporal chaos in multidimensional Hamiltonian systems. So, Harry, you can start.
Thank you, Sotiris. It is a pleasure to be with you, colleagues, and I would like first to thank the organizing committee and especially Sotiris for giving me the opportunity to share with you some of the research activities and results that we have obtained in recent years. So I will try also to be somehow pedagogical. I'm not sure that I will be able to stand at the same level as Tassos, but I would like to describe some numerical techniques which we can use in order to understand the chaotic dynamics of multidimensional systems. What Tassos showed was really very interesting. Of course, towards the end of his talk, he mentioned extensions to higher dimensions, but I will start also from the beginning with high-dimensional systems and how we can try to understand the chaoticity and nonlinear dynamics there using some different numerical techniques. So the outline of my talk is the following. I will focus on a particular Hamiltonian system, the Klein-Gordon system here. I hope that you can see also my cursor. And because I'm quite interested in the dynamics of this model, but what I will discuss can be applied to many different dynamical systems. So I will use, in order to investigate this model, I will use different techniques that many of them are known to the audience, like, for example, the maximum Lyapunov exponent, in order to quantify the strength of chaos and see how we can understand chaos using this quantity. I will also speak about something which is called deviation vector distribution, and this technique will help me to understand the mechanism of chaos inside this particular system. And then I will also refer to the frequency map analysis, which will be another complementary way of allowing me to understand how chaos is propagating and is performed, the chaotic behavior is performed in the model. And at the end, I will discuss another chaos detection technique, the so-called generalized alignment index, which, among other things, will allow us to discriminate between what I call localized and spreading chaos. So let's start with the model. The model that I will study, it has this following Hamiltonian. And the idea is quite simple. You have nonlinear oscillators that they are coupled. And you see here we have nearest neighbors coupling, kinetic energy, on-site potential, nearest neighbor coupling. All these black terms are linear. And then we have the on-site nonlinearity, this term, because here we have u, which is the position to the power 4. So this is a lattice, like in the similar sense that you have FPU lattices or other famous models, the discrete nonlinear Schrödinger equation, things like that. So we have nonlinear oscillators that they are coupled, and each one of them has a nonlinear potential, on-site potential. The other thing that it is important to clarify here is that this system is disordered, and I would explain what disorder means. So you see that L is counting the oscillators, the potential has this form, but here we have a parameter which defines the linear part of the on-site potential, which has a coefficient, this coefficient epsilon tilde. And this number is fixed for every oscillator, but not exactly the same. So what we are trying to mimic here is the heterogeneity that we have in nature. So we have a solid, for example, we have the atoms, but then there could be impurities, imperfections, things that change a little bit the dynamics from point to point. So that's what we call disorder, because if this epsilon number is the same for every side, then the model is called ordered. This does not mean that the motion is ordered or regular. It means that the model itself is ordered, is the same everywhere. But in this particular case, we have epsilons that they are chosen uniformly from this interval. And if we choose a set of epsilons, we put them in our model, these epsilons remain constant, we do numerical simulations and investigations with this model. This is what we call one disorder realization. And in order to understand the global dynamics or the more general dynamics of the model, we will perform similar simulations for another disorder realization, another sequence of epsilons, and we will have statistical analysis of these results. Typically, this lattice system has many degrees of freedom. Typically, we have 1,000 or 2,000 or even 3,000 lattice sites, which means that it is a very, very large Hamiltonian model. And of course, the phase space has many dimensions and it is difficult to visualize. So we will not try to do that. So this is the model. And again, this term is the nonlinear term. If we neglect this term, then we have some coupled harmonic oscillators, and we can go to the linear case, and of course, we can find the normal modes and the frequencies of the normal modes. And we know that if this term does not exist, and although disorder exists, this model will show what is called Anderson localization. The normal modes will be localized, and if the disorder strength is quite large, and the disorder strength is defined by this parameter W, because if W is very large, then this term can be somehow neglected, and this disorder term becomes more prominent and important. So W, you can think this W parameter as the strength of the disorder. The larger the W, the more important the disorder comes in our system. So if the nonlinear term is not present, we can have, for strong disorder, what is called Anderson localization, which is a very famous behavior, and of course Anderson won the Nobel Prize for that. And the main question that I would try to answer, me and my colleagues who have been trying to answer over the past couple of years, is what happens if we have nonlinearity, if nonlinearity is present, and if this nonlinearity will destroy localization. But also we will try to understand the process of chaotic behavior in this model. So how will you do that? So we will follow the evolution of energy. So what we will do is we have a lattice. Typically, we will excite some middle particles in the lattice, and we will see how this energy, this excitation is spreading. So we will have energy distributions, psi, the energy per site divided by the total energy. That means normalized energy distributions. This is the energy per site. And then we will compute two main quantities, among others, but the main quantities for understanding the distribution is the second moment. So the second moment is practically Tassos, you are not muted. So the second moment tells us is practically the standard deviation and tells us how far away is going the distribution. And another quantity which is important is what is called participation number. It is defined like that. And this number is telling you, giving you an idea of how many sites, how many oscillators are highly excited, have large enough energy. And we can easily see the two, So, and we can, I'm trying to put that, no, it's not that, in any case. So let's go back. Nope, the other one, here. And this quantity here, the participation number, is telling you, as I said, how many sites are highly excited. If, for example, you have equipartition of energy, this computation will give you N, the total number of oscillators. If we have single site excitation, which means that all the energy is in one oscillator, then this will give you 1. Of course, in real experiments, you will have something in between. But this number is an indication of indicator of how many sites are highly excited. So just a brief, I will try to make it brief, description of the different dynamical regimes that we expect, and actually we and other people and other groups around the world have already verified that we can expect in these models. So there are some quantities that they can define the fate of initial localized excitations. First of all, one thing is the width of the frequency spectrum of the linear system. You remember here we said that we can find the eigenvalues and the frequencies, the omegas, and if we compute that, we see that the omegas are in that interval. So there is a width of the linear spectrum. Another quantity which is important is the average spacing of interacting modes. This means the following. If I compute the linear modes, they will have graphical, this is just a graphical representation, a form like that. Don't forget they should be localized because we have Anderson localization. And there is a quantity which we call the localization volume, but practically is the participation number of this mode, and it tells you how extended is this mode. So on average, the modes are, the extent of the normal modes are defined by this quantity, and then if we divide the spectrum with this quantity, we have, on average, again, an understanding of what is the spacing in the spectrum of the different modes. And then, of course, the question is what happens if we introduce nonlinearity. So if we introduce nonlinearity, we will see that at the first approximation, the nonlinear shift of the frequencies, delta L, is something which is proportional to the energy. The energy, the total energy, the Hamiltonian, is a parameter which describes the nonlinearity strength. So we have these three quantities, delta, D, and the nonlinear shift. And we have established also theoretically, but we have also verified numerically in more than 10 years now, different dynamical behaviors, which we call, the first one is called the weak chaos regime. And in this case, the nonlinear shift is rather, it exists, but it is small. And what happens in this case, the theoretical prediction, which, as I said, again, has been verified, is that the second moment is increasing in time following a power law with this exponent, and the participation number has another well-defined power law. And we call that weak chaos exactly because the nonlinear strength is rather weak. And there is another regime. If the nonlinear shift is between these two quantities, the D and the delta, then we have a faster increase of the spreading of the wave packet. The exponent, instead of 1/3, is 1/2. And the participation number has another exponent. And this is somehow an intermediate state, which could last for very long. And eventually we see a crossover to the previous weak chaos regime. When the wave packet spreads enough, then the nonlinear shift becomes smaller because, don't forget, the total energy is conserved. So the energy of the whole wave packet is spread to more and more sides. So things will decrease, and eventually we will have a crossover. But this crossover to the weak chaos regime behavior, which is characterized by a different exponent, might take a very long, and typically takes quite long. And another regime which is not that interesting for us because we are more focused on the spreading of the energy, not the localization of the energy, is what is called the self-trapping regime. If the frequency shift is large enough, and it is large enough so that it tunes out the frequencies from the frequency band, then we have a big part of the wave packet remaining localized, although some tails will propagate. So what I would like you to keep in mind is that we have established two different dynamical behaviors, different in the sense that they are characterized by different exponents or rates of spreading, what we call weak chaos and strong chaos. And these two dynamical regimes will be the focus on this presentation. We will try to understand how chaos is actually manifesting itself in these behaviors. So, as I said, what we are typically doing is the following. We start with some initial excitation at the center of the lattice, like here. We let time evolve, and we see that the energy is spreading. And we do that for many disorder realizations, different values of different arrays of this epsilon tilde that I mentioned before. And what we do then is we measure the quantities, the second moment, and the participation number. Here I'm presenting the second moment, and this is just to verify to you that the theoretical predictions that we had previously, sorry, the other way, here, the exponent 1/3 for the weak chaos regime and 1/2 for the strong chaos regime actually can be seen in the numerics. And here we see the average second moment and average is done over 1,000 realizations. Here we evolve the system of 1,000 degrees of freedom for 10 to the 9 time units. That's a huge computational task, and we repeat this computation for 1,000 times. And here is the results that we get. This is the weak chaos case. This is the strong chaos case. The red one is the self-wrapping, where it's not very interesting for us at this stage. And on the bottom plot, we just compute numerically the slope of these average curves. And you see that eventually for the weak chaos case, the slope saturates to 1/3. In the strong chaos case, we reach the 1/2, and then we have this tendency to go back to 1/3. And here, this is a schematic representation in the parameter space of W, the disorder strength, and the energy, which defines the nonlinear shift, where these two spreading regimes and the self-trapping regime exist. And this is something that we will come back later. So this is the type of numerical simulations that we are doing. We excite something in the middle, even one side in some cases, and we follow the evolution of this energy profile as time goes on. Now, since this is a chaotic system, because it is a nonlinear system and nonlinearity is present, we can quantify somehow the strength of chaos by computing, which everybody in the room, I'm pretty sure, know the maximum Lyapunov exponent. So what we do actually is we take an initial point in our phase space, which is an initial condition, we perturb it a little bit, or we consider a small deviation from that, considering a deviation vector in the multidimensional phase space, and we compute the evolution of this deviation vector. We divide the lengths of the vectors at different times, take the logarithm 1/t, and if this limit exists when t goes to infinity, of course numerically you cannot do that. You just compute this quantity lambda capital as long as you can. The limiting value of this quantity will be what is called the maximum Lyapunov exponent, and the maximum Lyapunov exponent can identify the nature of the evolution, if it is chaotic or not. For example, if it is positive, then the motion is chaotic. If it is 0, of course, you will not find 0. You will find something, a decay of this indicator lambda to 0 with a slope which is in log-log scale characterized by -1. So that means that power law decay. This is a nice and well used and known indicator. Let's see what happens in our case if we evaluate that in our case. So this is an example in the weak chaos case. This is a particular disorder realization. We follow the evolution of the second moment. This is the computation that we get for the second moment, the participation number, and we see that the slope 1/3 and 1/6, well, which was predicted also by the theory, is well reproduced there. Here you see the wave packet at the end of the integration after 10 to the 9 time units in log scale. So you see that there is something which has spread enough, but then we have some exponential tails. And here is the evolution of the Lyapunov exponent. So after some transient initial phase where the Lyapunov exponent shows some tendency to decrease with the slope -1, this curve. Don't forget that a slope -1 in log-log scale for the Lyapunov exponent means that the Lyapunov exponent, that the motion is regular. We see a deviation, and the Lyapunov exponent is decreasing, but on the other hand, which means that chaos becomes weaker, but on the other hand, we see some tendency to decrease with a different power law. And then we can also quantify that even more by doing some statistical analysis. And here we have results, average results over 100 realizations for different parameter sets. These sets belong to the weak chaos case, these belong to the strong chaos case, and we see that in all cases, the average evolution of the Lyapunov exponent show a tendency to decrease with a slope which is different from -1, like in this case. But now this was just one realization. So you see here that the slope is well approximated by this number, -0.25. And if we compute this numerically, the slope, you see that these slopes actually go to 0.25, while in the case of the strong chaos, we have a different number. And this is general because different arrangements of the parameters of the model, different energies, different Ws, different type of initial excitations, all that we predict that they should belong in this particular dynamical regime have the same numbers, but these numbers are different. So one important outcome is that we can have the Lyapunov exponent decreasing to 0, but with a slope, with an exponent which is not -1, which will signify regularity. Like here, we have these two different distinct numbers, and this means that the system is chaotic, but chaos becomes weaker and weaker. And the reason is rather simple, because we start with some initial excitation, which was at the center, and then the fixed energy is spreading to more and more degrees of freedom. Although the system has, I don't know, in this particular case, I think it is 1,500 degrees of freedom, not all of them are excited from the beginning, only a few, because the energy is concentrated somewhere. So for example, these sides are unaffected. So although the system has many degrees of freedom, only some of them have been excited. So the effective degrees of freedom are changing in time. And this is translated into the fact that the Lyapunov exponent is decreasing because the energy is distributed to more and more sides, but it is decreasing with a slope which is different from -1, and that's a clear sign that the system is chaotic, but the chaoticity is becoming weaker and weaker in time. So that's an interesting way of seeing the evolution of the Lyapunov exponent. Another idea that we explored in order to understand how this chaotic behavior is happening, how the chaoticity is pushing the wave packet further and further, is the following. In order to compute the Lyapunov exponent, you remember that you need a vector. So you start with a random vector, deviation vector, which points to a nearby orbit, and you see how this vector is evolving in time. And here we are interested only in the length of the vector in order to compute the Lyapunov exponent. But what I would like to do is, I would like to see also the evolution of the vector as a distribution. So what I'm doing is, I'm taking the vector has coordinates in the positions and the momenta, and for every degree of freedom, for every oscillator, I find the projection of the vector on that space. So actually I compute what I call the deviation vector distribution by taking the projections of this vector, the coordinates of the vector at site L, divided by the total length of the vector. And this is a distribution. And here you see, for, again, the same example that we had here, here is the energy distribution at the end of the integration. Here we see the distribution of the vector, of the degrees of the vector, of the coordinates of the vector. So why we are doing that? This vector is defining the maximum Lyapunov exponent. So it is giving you the direction, which of course changes in time, of the most unstable behavior of the system. And in some sense, the sites where this vector has a larger projection, the oscillators that the vector has larger projection, are at that time the more unstable or the more chaotic. So we are trying to identify chaotic hotspots inside the wave packet. So we see, first of all, by just looking at this projection, these distributions, that the deviation vector is definitely more localized. Don't forget, here we have log scale, so these are orders of magnitude smaller. So it is more localized on the energy profile. And actually what we will see in the next slide is that this localized form remains more or less the same, but it is moving inside the wave packet. So let's see here results for the weak chaos and similar results for the strong chaos. Let's take the strong chaos because it is probably easier to see. So what do I have here is, for a single disorder realization, the heat map of the evolution of the energy. So these are the sides. I excite the middle side, and this blue region tells me where is the wave packet, and I see that the wave packet is spreading. This white line is defining the middle of the wave packet, and here I take some snapshots. At the green, I have this form of the wave packet. Black, at some later time, you see that the wave packet has spread a little bit more. Again, this is in log scale, and red at the latest stages. So we see that the wave packet is spreading more or less symmetrically, although the system is not symmetric because the different epsilons have different values. If we do the same thing for the deviation vector distribution, we see this kind of behavior. So you see this, the middle point is starting having quite fast and big oscillations, and which means that the wave packet, the deviation vector is moving inside the wave packet at different times. So you see here at the same times the profiles, and the profiles more or less look the same, but the peak is moving inside the excited part. So what is happening is these chaotic hotspots are moving, not all at the same, all times the same oscillators are chaotic, but this moves, and this in some sense supports the homogeneity of chaos and the spreading of the chaotic of the wave packet. And we can do also some analysis about the characteristics of the DVD. So we can also compute the participation number, the second moment of the DVD in both weak and strong chaos cases. And we see that what we have experienced also here, that the participation number is practically remaining constant. So the shape more or less remains the same and quite concentrated. And another thing that we can do is we can somehow try to quantify this motion inside the excited part, which is helping the mixing by measuring a quantity which tells you how far in the right and how far in the left the wave packet went. And what we see is that this quantity is increasing in time, which tells you that the wave packet is moving more and more as the DVD is moving more and more inside the excited part. So this mechanism somehow is feeding the chaoticity and helps for the wave packet also to spread, because the wave packet is spreading. Now, trying to understand a little bit more how exactly this is happening, we can use another method, another numerical computation, which is called the frequency map analysis. The idea behind that is the following. If I have regular motion, that means quasi-periodic. So if I take a signal from this regular motion and compute with some Fourier analysis the frequencies, let's say the main frequency of the system, of this signal, this frequency should not change if I take one time window and the next time window. So what we do is we compute what we call the fundamental frequencies, the basic frequencies, F1 and F2, into successive time windows. And if we have regular motion, obviously this frequency should not vary in time. Of course, we do numerical computation, the frequencies will not be exactly the same, but their difference should be small. On the other hand, if the motion is chaotic, there is no signal, there is no periodicity there. Of course, you can always take a signal and compute the frequency. So if you compute the two frequencies, they will be different. So the computed frequencies in the two successive windows, time windows, should vary in time. And that's another way of indicating if the signal or the dynamics behind that is chaotic or not. So what we do is we compute exactly this quantity. We take, now we have our system with 1000 degrees of freedom. For each one of these oscillators, we compute a quantity which is defined by the positions, the momenta, actually Q square and P square. We compute the frequencies of this signal for every oscillator. The differences, we also normalize it with respect to the frequency in the first part, because it is important to see if the difference is small or big relative to the frequency itself. And we create this quantity which we call D. If we have regular motion, the D value should be very small, because these two frequencies should be practically identical. While large values for D means chaos. So let's see what we can compute what we get if we do this computation. So here we have results for the weak chaos, one particular case, and the strong chaos. Let's focus here. So what we see here is the following. We have the sides, the excitations happen at the middle, and here we see time, and we see that the energy is also spreading. And for two successive windows, we compute the frequencies, we compute the difference, we evaluate this d value, and take the logarithm, and using this color bar, color code, we color the sides according to this d value. And I remind you, large values, yellow, red color means big differences, which means chaos, and small values means that the two quantities are practically the same, which means regularity. And here we have the time window from 0 up to 10 to the 8, and here it's from 9, 10 to the 8 up to 10 to the 9. So the same time interval, and we see how things change. And it is obvious that at the borders we have regular motion because the frequencies do not change much, while at the center is more chaotic behavior because these differences are higher. And if you compare this plot and this plot, we see that obviously the extent of the chaotic behavior and the colors are brighter, which means that in the case of the strong chaos, more oscillators are chaotic in the middle or in the middle parts, and the extent of this region is larger with respect to the weak chaos. So at the borders, we have more or less oscillators that they are behaving regularly until they get enough energy that they become part of the main body, and then eventually they also have chaoticity. And this is a nice picture, but we can also quantify it a little bit more. And here we do something along these lines, which is a little bit more complicated. So what we do is, instead of computing actually the frequencies with high accuracy, we just create bins in the frequencies of width 10 to the minus 4. So we reduce somehow the resolution of our frequency. So we have bins of width 10 to the minus 4, and what we do is we evolve the system, we compute the frequency for every side, and let's see what we compute for each one. At a side, we compute the frequency, and we see in which bin this frequency belongs. If in 2 successive times or 3 successive times or in time, the same frequency is registered in the same bin, that means that the frequency, although it might change because the width is 10 to the minus 4, remains more or less at the same in the same value, what is called frequency locking. So we are computing for a time window the percentage of this kind of frequency locking, which means that the frequency there was more or less constant. So this quantity, frequency locking, means is something which will be from 0. The frequencies change very fast, or 1, which means in this window all the frequencies were in that particular bin. So the frequency were practically constant, which is a degree of regularity. And then from time to time, we start the computation again. That's why here in this plot you see this kind of vertical lines. And the reason is the following. We want to explore if in the evolution there are some time windows where the frequency is more or less constant at some value, then it changes. Don't forget the system is chaotic, but again, we have some kind of constancy for another time window. And black regions mean that the frequency locking is quite high, regular behavior, and this yellowish or purple color means that we have many changes. The frequency locking is smaller and means we have chaoticity. And you see more or less what we had seen before, that in the middle part we have more chaos because we have these colored plots, colored points, while the black points identify regular motion. And another thing is that for the strong chaos, we have more extended chaos. And if we compare these two time windows, this is a later time window, we see that the colors become darker, so that means that the nonlinearity is spread, but it becomes weaker. So this is another way of quantifying that. And and we can also quantify it in the following way. We compute here the percentages of sites that they have the frequency locking parameter, this quantity, at different intervals. Smaller values means more changes, means chaoticity. So for example, the yellow and the orange is giving you the more chaotic sides, the sides that they have more changes in their frequencies. And we see here weak chaos, here strong chaos, first time window, later on, that in both cases, the percentage of strongly chaotic sides, that they have many changes in their frequencies, this orange, let's say, color, is decreasing. So this is another way of seeing and quantifying the fact that the dynamics is becoming less and less chaotic, but not approaching a regular behavior. And another quantity that we used in order to attack the same problem from a different angle is another chaos indicator, which has some advantages, as I will tell you in a minute, with respect to the Lyapunov exponent, which is called the Generalized Alignment Index. So the idea here is the following. Instead of following just one deviation vector and compute the Lyapunov exponent, we follow more initially linearly independent deviation vectors. So we can have, in a system with n degrees of freedom, we have a phase space of 2n. So we can have from 2 up to 2n vectors and deviation vectors. So we follow the evolution of the orbit, we follow the evolution of more deviation vectors, and we normalize them from time to time, and we compute the volume that they define, these vectors. This is what we call generalized alignment index of order k. So we define the volume. Look, what happens now if you have regular or chaotic motion? If you have chaotic motion, then we know that in principle, no matter what is your initial deviation vector, you will always find the same maximum Lyapunov exponent. Why? Because the two vectors, or the three vectors, or any vector will eventually be aligned with the direction of the largest Lyapunov exponent, which is what we call the DVD in previous slides. So if we have this orbit, our initial point, next point in the phase space, we start with two vectors, we let them evolve there, trying to become closer because they are tending to the same direction. We normalize them and we compute the volume, which means the area in this case, and we see that the volume is decreasing. So in chaos, this quantity should decrease, and we will see in a minute how. If we have motion or regular motion, then we have motion on a torus. This is the point. Later on, we start with two vectors. These vectors, the dynamics will put these vectors on the tangent space of the torus, which is represented like that, and eventually they become closer and closer to the tangent space, but there is no need for them to become aligned. So chaos means that the two vectors or more vectors will become aligned, and the area, the volume, should tend to zero. And this is exactly what we observe, and this is also theoretical predictions which have been verified numerically. So this quantity, Kali K, will decrease to zero if we have chaotic motion with an exponential rate, and this exponential rate depends on the k largest Lyapunov exponents. So lambda 1 is the maximum Lyapunov exponent, lambda 2 is the second Lyapunov exponent, the third, and the kth. So a very fast exponential decrease of Gali k to zero means that the orbit, the behavior is chaotic. On the other hand, if we have regular motion, then, as I said earlier, the vectors will fall on the tangent space of the torus. But if we have an n-dimensional system, the torus is n-dimensional. So if we start with k vectors which are less or equal to n, they will fall on this n-dimensional space, and there is no reason for them to be to become linearly dependent, so the volume will not vanish, so this will be more or less a constant value. But if we have more vectors than the dimensionality of the tangent space, which is n, then eventually this will become linearly dependent and the volume will also vanish in that case, but with a behavior which is completely different from the exponential decay, which is a power law decay. But we will not be interested in that, so we will do the simplest thing. We will take only two vectors because it is also computationally easier to have two vectors instead of many for our system. And for these two vectors, we expect that for chaotic motion, Gali will go to 0 with an exponent which depends on the first and the second Lyapunov exponent, and Gali for regular motion will become constant. And actually, Gali 2 is what is another name for the first version of this index, which is called the smaller alignment index. So let's see now how we can use that in order to understand the behavior of our system when the nonlinearity, the total energy, becomes smaller and smaller. So we want to investigate how the system behaves when we are approaching the linear limit. So what we do here is we have a particular case, a particular arrangement. We have W equal to 6, strong nonlinear and strong disorder strength. The energy is small, and we do single-side excitation. So in this framework, we explore many different disorder realizations, and we can find different behavior for the same parameters. So here is one case. We do the single-side excitation, but for one disorder realization, and we observe, we did numerical simulations for more than 1,000 cases, and here I have some representative cases. So here you see the second moment remains constant, the participation number remains constant up to 10 to the 9, and the Lyapunov exponent goes to 0 with a slope which is very well reproduced by -1, while Gali is up here, remains constant. So that means that the motion is regular. So we were able to find a disorder realization for these parameters for which the single-side excitation just gives regular behavior. And you see that this regular behavior here. This is the energy profiles at different times, 10 to the 5, 10 to the 7, 10 to the 9, and you see that the profile is practically remaining the same. So regular motion. Now, we change the disorder realization. We take some other random values for epsilon in the same interval, and we have this behavior. The second moment and the participation number remains constant. So that means you do not have spreading, because this quantity tells you if you spread. So we have localization. But if you compute the Lyapunov exponent, you see that eventually the Lyapunov exponent deviates from this slope -1. And towards the end of the computation starts to increase. So this is a clear indication that the system is chaotic, is not regular anymore. But of course, in order to realize that, you have to really plot the evolution of the Lyapunov exponent. But if you compute the Gali, you see that the Gali becomes abruptly 0. This is 10 to the -8. So quite fast, it goes to a very small value. So for this particular case, it is not, of course, we saw the evolution in order to understand what is happening. But if I want to see if the orbit, if this particular evolution is chaotic or not, what I have to do is just register Gali and see if Gali becomes smaller than 10 to the -8. It is not necessary for me to plot this evolution. So if you see the profiles, we see again that more or less the energy remains localized, but on the other hand, chaos is happening. So there is some chaotic interaction. Another disorder realization. So here you see that towards the end, for the same parameters, towards the end of the evolution, we see some clear increase of the second moment and the participation number. Again, a deviation of the Lyapunov exponent from the slope -1, and a very abrupt decrease of Gali. So these two quantities tell you that you have spreading. These quantities tell you that you have chaos. So we have spreading chaos. And again, if you see the profiles, here you see that we start with something which is the red one, which is localized, but the black one has extended more. So using the Galley technique, we can easily identify chaoticity quite fast without even having to inspect the evolution of the index, and we can discriminate, of course, with the computation of the second moment of participation number, between different behaviors, regular motion and different types of chaos, localized or spreading chaos. And what we did is we consider single site excitations and single mode excitation. So we take the linear mode and we excite the linear mode, but in the nonlinear system for different values of W, the disorder strength. And we compute the percentage of chaotic orbits as they are quantified through the Galley computation as the energy is decreasing. Here is the logarithm of the energy, and we see that we go to smaller energies. And what we see here is that there is an energy threshold that all the disorder realizations above which all the disorder realization will lead to chaos. So everything is chaotic. No, we were not able to find in 1,000 random disorder realization a single case that was giving you regular motion. But as we decrease the energy, going closer and closer to the linear limit of the system, we see that these percentages are decreasing. So for this energy, for example, 50% of the disorder realization that we checked were chaotic and the other 50 were regular. And eventually you see that everything, this is the percentage of chaoticity, everything becomes to regular. The same is also happening also for single mode excitations, but the thresholds are larger. For example, here, at 10 to the minus 2, energy 10 to the minus 2, there is practically no realization which gives you chaos. While for the same system at 10 to the minus 2, 50% or 60% in the other case, you have chaotic behavior. The reason between this difference is the following. If you do single site excitation, like it or not, you always excite more modes. So there is some mode interaction, and this is the key point in order to have chaos, the interaction between the nonlinear interaction between the linear modes. But if you have a single mode excitation, then you just have this mode and the interaction introduced due to the presence of nonlinearity of this mode with other modes is very small. That's why you need larger energies in order to see chaos. And then we can also do a more detailed analysis about the chaotic cases. So we can find, as we decrease the energy for the different W's, here we have single site excitations, single mode excitations, how many of the chaotic cases are localized chaos or spreading chaos. And we see that for larger energies, all chaotic cases are spreading chaos, while there is a bulk of localized chaos as the energy is decreasing. So as we go to smaller energies, less and less cases of chaos appear, and more of them are localized chaos. So spreading is not present. Sorry. Yeah, and I think that I'm on time. So just a small summary of what I presented. I was trying to understand the dynamics and the characteristics of chaos for a particular model of disorder lattices, the Klein-Gordon system, and a particular, if you want, type of excitations at the middle, and I was trying to understand how the energy is spreading. But the different techniques that I use, the different approaches, can be also applied to different models. So we saw that we had two different dynamical behaviors, and these two different dynamical behaviors, the weak and strong chaos for this particular case, had different characteristics through all the indices that we used. The Lyapunov exponent, which tells you the strength of chaos, is decreasing, but with a slope which is not -1, which will mean regularity, and the exponent is characteristic for each case. The deviation vector distributions can show you, can reveal the chaotic hotspots which are meandering inside the wave packet and help in the mixing and the homogeneity of chaos. The frequency map analysis can visualize the regions and the extent of and strength of chaoticity. And the galley can also help you to discriminate quite fast and efficiently between localized and spreading chaos. Thank you very much for your attention.
Okay, thank you very much. So I see already there's a question by Professor Bundis. You have to switch on your microphone.
Yeah. Hi, let me ask you, this is a very nice, thorough quantitative analysis of the phenomena that you discussed. What I want to ask you is if there was a certain phenomenon that surprised you. In other words, some kind of phase transition, if you change the W's abruptly, or you vary some of the parameter approximately, do you see something surprising, a change, a global change in the behavior of the system, like a phase transition, for example?
Yes. Well, for the parameter values that we used, we do not have this kind of strongly surprising behaviors, but what I tried to explain in that direction somehow is how we reach the linear limit of the model. And this is what I try to do here. And this behavior is also somehow has some kind of a random content there, because for the same parameters, you are able to find different disorder realizations which can lead you to different behaviors, from regular to spreading chaos and localized chaos. And that's what we try to investigate here, how as we are decreasing the energy, we can have different behaviors coexisting. Regularity, chaoticity, and different kind of chaoticities, actually, spreading or localized chaos. So the main thing that we'll try to understand is how chaos is propagating and introduced in these models, and how it is helping the spreading.
Okay,
So,
thank you. Mm-hmm.
Thanks.
Okay, any more questions or remarks? Okay.
I think we have an echo, but I'll ask the question anyway.
Yes,
Professor
please.
Buntis, I think you need to disable your microphone. Thank you. Yeah, so apologies in advance. I worked in this area a long time ago when I was an undergraduate. So that epsilon, the parameter in the Hamiltonian, which represents disorder of the lattice. So if I remember correctly, you have a uniform distribution, yeah, for it.
Yes.
In that interval. So do you have any idea what will happen if because disorder in solids, it comes, it has many different phases. So what would happen to the chaotic behavior if you choose a different distribution, if it makes sense?
Okay.
Thank you.
Yeah, that makes sense, actually. And this is a nice question. And we have not extensively studied that, but we have done some preliminary investigations using Gaussian distribution. Again, something which is centered at the middle of this interval and extending quite until the edges. And we didn't see, let's put it this way, really big deviations from what we showed here, because the bulk of the Gaussian distribution was in that region. In some sense, it was covering the same region. But it was not exactly the same. But we didn't investigate further. But yes, it will be interesting to use different distributions for the epsilon and see what is the effect there. But what I can tell you is that for normal distributions, we didn't see big differences. We more or less have the similar results, but we did not investigate further using other kind of distributions. Thank you.
Okay, thank you. Any more questions or remarks? Okay, in which case, let's thank the speaker again. Thanks very much, Haris.
Thank you so much.
So, okay, we have a coffee break until we meet again at 11:20. So it's my pleasure to present the next plenary speaker. So it's Eleni Christodoulidis from Lincoln University of Lincoln in the UK. And she's going to be talking about the impact of adiabatic invariants on the dynamics of the Fermi-Pasta-Ulam, what is the, I don't know, model. So Eleni, you can start.
Thank you very much, Sotiris. It's a pleasure to give a talk at the Satellite International Conference. And thank you very much for the invitation. So about the title is the impact of the adiabatic invariants on the dynamics of the so-called Fermi-Pasta-Ulam-Tsinghou model. So this T has been added quite recently for the contribution of Mary Tsinghou, who did all the simulations of this particular model. However, she was neglected in the publication. So I think it's better we add her name as well. And before I start my talk, I would like to say that this problem that is quite applied is a fundamental problem of statistical mechanics. It, on the other hand, it greatly inspired the birth of integrable systems, and that was done through the famous paper of Zabuzki and Pascal on the KDV equation that was inspired to solve this particular problem. So there has been done a lot of progress over the years on integrable systems. However, in this particular problem, there's still things to be done, and this so-called paradox that I'm going to talk today is still an open question. So the aim of this talk is now going backwards to apply integrable systems theory in statistical mechanics in order to get some results in this fundamental problem. So in short, the talk will introduce what is this problem and the approaches that have been done, and it will essentially focus on its relevance to the integrable model, the TODA model, and moreover, the main interest is to focus on the TODA integrals that can be used as observables for the Fermi-Pasta-Ulam-Tsinghou model, and they can be used in two ways. First of all, that they will be the adiabatic invariants of the system of the non-integrable Fermi-Pasta-Ulam-Tsinghou model, and secondly, as indicators about ergodicity. And I will present some comparison with other indicators as well, which are very important, and I will conclude with some numerical results. Just a question, can you see the little hand moving around?
Yes, you can see it, yes.
Okay, so just to be able to show. So what is this problem? The problem that was inspired initially by Fermi in 1954, that was when he was working with the other colleagues, that is Pasta, Ulam, and Mary Tsinghou in the Los Alamos laboratory. And they considered a chain of harmonic oscillators initially. So if you consider that this is a chain of linearly coupled harmonic oscillators, we well know that this is the kinetic energy. So these are the momenta squared over 2, and this is the potential energy of the harmonic oscillators. That is the relative difference of their displacements from the equilibrium position. So Qn is the displacement from the equilibrium position of the nth oscillator. And now they considered this model, and they added a perturbation, a cubic perturbation to the potential energy. So they consider that this parameter here is relatively small, and what was the question is to show that now this system will be ergodic, and we'll slightly explain to what is what ergodic means. So just to mention that at that time, the integrability didn't exist as a concept, and it was about the same time that Kolmogorov, Arnold, and Moser developed the famous KAM theorem. So it was not known at that time. So this was the initial experiment that merit single performed. So this was in one of the earliest computers, so it was a massive computation at that time. They considered 32 particles, and they considered as observables to test ergodicity. They wanted some observables, so they considered, simply to say, the integrals of motion of the harmonic oscillators. So this EK is, so the Hamiltonian of the harmonic oscillators is the sum of all these integrals, EK. These are the new positions and momenta with capital letters that decouple the harmonic oscillators. They are not anymore constants of motion for the perturbed system. And to show that it is ergodic, they need simply this equation, that the time average of an observable is equal to the ensemble average. And in simple words means that for all EK, if we take the time average of that, this should, in statistical equilibrium, this should converge to the total energy divided by the number of particles. That is called the specific energy. So in other words, all EK, they should tend to the same value, the equally shared energy among the so-called normal modes. And they started by this initial condition. All the energy was placed on the first normal mode, so this is E1 essentially. And instead of observing ergodicity, they observed quasi-periodicity, that a few of them, like say that roughly the next 5 normal modes received some energy, which, however, they gave back to the first normal mode, so you have this quasi-periodic solution that is in contrast to the expectations of Fermi. So this is how the beginning of the paradox. This omega k are the harmonic frequencies, and if you take the time average of these observables, so you get now a constant value because they are quasi-periodic, so you smooth out the oscillators, the oscillations, and you get some value that apparently are these values of all of them, so EK versus K, are exponentially localized. So they're exponentially localized in the normal mode space, and this is in contrast to their expectations. They expected to have a flat energy spectrum, but this didn't happen. So now there have been hundreds of works done, not to mention, as I said in the beginning, the Zabusky and Kraskal paper, or the most famous maybe. I will not mention them. There's too many works have been done and books published, just that different approaches, some of them find the same results. So if we consider that the Hamiltonian FPU is a perturbation of the harmonic oscillators, and so this H0 is the Hamiltonian of the harmonic oscillators, and here's the cubic perturbation of the potential. Now the left side is, they try to find a cutoff energy where below that you observe integrable-like behavior, like it can be CAM style, so you can have full dimensional tori or a low dimensional tori, or something that you have quasi-periodicity or even periodicity or single periodic orbits. Anyway, you have stability. Now, above the cutoff energy, you expect to have chaos and ergodicity, and so they're trying to find, the left side tries to find like the maximum value of the energy by analytic means, while on the right side, the famous Chirikov resonance overlap criterion was developed to solve exactly this problem, wanted to find a minimum value of the energy, above which you have definitely chaotic behavior. So nice two sides that have been developed over the years. And just to mention, for high modes was done in a nice paper by Israelov and Chirikov. For low modes was done later on by Sepaliansky, who is a student of Chirikov. And now both sides, many authors from both sides, they find that by analytic means that this energy cutoff goes like that. So 1 over the number of particles to the power 4. So we could say that, okay, the problem has been solved. This means that since this crossover decreases quite fast with n, means that in the so-called thermodynamic limit where n goes to infinity, you expect this to vanish quite quickly. So just to give an idea, what does it mean in terms of numbers? For the original system where you have 32 particles, if you do the computation, it gives you something like 10 to the minus 6. So something that's really small. So 10 to the minus 6, something, a really small number. In the original experiment, they used an energy, a specific energy that was about 10 to the minus 3. That was quite large. So if we plot them in a logarithmic scale, here's the theoretical expectations, what we find by perturbation theory, and here's what we find with a numerical experiment, the original one. So this doesn't explain, this quasi-periodic behavior has not been explained by theoretical means, and is a big question why. So it is a question why for 32 particles, but the essential question is what happens for any n value, what happens for larger systems. And I would like to point out this paper by Sokolyansky that himself, he proved this law for the FPU system, but however, he criticizes that these nice theoretical estimates based on the Cherenkov criteria cannot exclude the possibility that the system under investigation in general can be completely integrable or very close to some of them. So at that point is where if your system is too close to another integrable system is where the Cherenkov criteria fails in the sense of when you regard the harmonic frequencies at least, so when you regard it as a perturbation of the linear system. This point is very crucial for this particular problem since at low energy it's very close to the total lattice. So here comes the total lattice actually, and this is the point of this talk. So the Cherenkov criteria works very well for other systems as well as for another system called beta FPU system, but not for the alpha case.
Eleni, could you please say what means completely integrable in this context? Because for most of us, complete integrability is Liouville integrability, so that you have enough integrals in involution with respect to Poisson bracket.
Yes. So I assume, because I didn't write this paper, but I assume that Sokolyansky means Liouville integrability, completely integrable.
Yeah, okay, it's probably the same. Yeah, okay, thank you.
For example, for the Cherenkov criterion, you can read also in Wikipedia that if you regard the Toda model, as which is completely integrable in the Liouville sense, and you regard it as a perturbation of the harmonic oscillators, then if you apply the Cherenkov criterion, you will find the same 1 over n to the 4. So you will find that the system will be chaotic above an energy, which is nonsense for the total system. So when can we use the Cherenkov criterion? When the system is not integrable and when the system is not close to another model like Toda, for example. Okay, so this is why it doesn't work for the Fermi-Passa-Ulam-Tsigou model. Mm-hmm. And yes, please?
No.
Okay. So now back to the question, what is this critical energy? What is this energy crossover below which we do have this integrable-like behavior? Or we might not have exactly integrable-like behavior below the critical energy. We might have very weakly chaos, but in the sense of Nekh-Khorosev. That means that, in the sense of Nekh-Khorosev means that you might have a region of Cantori below that energy, and you might not be on a torus, you might be within, between two tori, so you might have what is called the Arnold diffusion, so you might have exponentially long times for the system to exit this stability region and to reach equipartition. So below we mean both cases, exponentially long times to equilibrium or completely being on a torus. Above that, you have clearly ergodic behavior. And the very heart of the problem, so the problem says, how does it depend on the system size? So here's the work that I would like to point out first. That is the work by Ferguson, Flaschka, and McLaughlin, published in '82, that they regard FPUT as a perturbation of the total system. And I will simplify a bit the Hamiltonian. All alpha have been considered to be equal to 1 to simplify a bit the parameters. And if you regard this Hamiltonian where the potential energy is this exponential, and -1 is just to remove some constants. And if we expand in Taylor series, so this delta Qn here that appears here is the relevant difference. When you expand in Taylor series, 1 with 1 cancel, the linear terms, the sum of them is identical equal to 0. So you start with the quadratic term so the potential plus the quadratic term gives you the harmonic oscillators, Hamiltonian. If you go on to +1 term, you get the FPU Hamiltonian. And so you can consider that the FPU Hamiltonian is a perturbation of 4th order in terms of delta Qn, and not of a cubic order when you write it with regard to the linear system. So you were on one step beyond. You are in 1 order higher, and that's quite important. This is, of course, doesn't make any sense, this pictures I'm showing now, but just to give a contrast. So if you regard FPU as perturbation of the linear system, this is the original FPU experiment. The harmonic oscillator, this is the constant of motion. Of course, it will never change. All the other modes are 0, and it will stay like that. Now, if you consider these variables, the energy spectra in TODA, and you repeat the same experiment, same numerical experiment, we'll see that they are identical with the FPUT system. As it is coined in the paper, the difference in the energy spectra are of the size of the line of the pen. So it's really, what we see is a total behavior in the FPUT system. And this paper apparently has been slightly forgotten and was revived later by Pono and Tal, Benetin, and other authors. The results I will present are mainly done from me and in collaboration with Christos Efthymiopoulos from the University of Padova, and about the total integrals that are adiabatic invariants. This has been proved for the first, for an amount of total integrals. This has been proved by Tamara Graba, who's the next speaker, and it's a nice, very nice paper. So I guess I will pass a bit quickly this slide about the L matrix. You know very well that it has been proved from by Henon and Flaschka that TODA has n constants of motion, and this can be found by the trace of this L matrix, whose diagonal terms are the momenta, and these A and variables are half of these exponentials. Just one difference with regard to these papers is that, in particular, in our case, we consider the fixed ends. So we don't regard the periodic boundary conditions. So we need also these symmetry conditions to apply to this matrix before taking the trace. And so the trace of the powers of the L matrix give us the integrals of motion. And in the particular case of fixed boundaries, the odd integrals, so the odd powers give exactly 0. And we have a system of half the size, or half integrals, which are the trace of the L matrix in even powers. The very first one, J2, that's a trace of L square, gives the Hamiltonian of TODA. And just the next one, which is the 4th power, is the one that we employ as an adiabatic invariant and as well as an indication of ergodicity. So this is main focus of this talk is on J4. So for simplicity, let's call it J. It's the first non-trivial integral. and it gets this complicated bit expression if you find it analytically, and divided by n. We divide by n, so we call it j for simplicity, and we divide by n+1, that's the size of the system, in order to make it intensive quantity, not to every time we change the system size, we don't want it to be proportional to n. And so this complicated expression, I will just simplify a bit to see what is the mechanism in this J, because we're interested to show ergodicity in the Fermi-Pastorlam single model. So we said that this AN are these exponentials, and what we're interested to see is what is exactly the first terms. What are the first terms? The first terms tend to be quadratic, so it has no constant terms. We would subtract the constants, and has no linear terms. They are all identically equal to 0. So by expanding this exponential interior series and applying that inside, we find that the quadratic terms, so the lowest order terms, get this expression. It's simplified. So this part here, which becomes here, we simplify a bit the calculations, and we get this expression. Now, if we looked at this Pn square and delta Qn square, actually give us the Hamiltonian of, they give us 2 times En, I mean the energies of the normal modes. So another simplification, okay, this is an approximation, of course. And so the quadratic terms approximate J to a good extent in terms of statistical mechanics. And so we're left with these 2 terms. So what are these 2 terms now? If we take the Sine Fourier transform as we did to go to the normal mode space, so with this Q capital and P capital variables, so we find that we can write that in terms of the energy spectra. And what we get is that the Toda integral, the lowest order terms, is approximately 2 times the specific energy, 1 over n+1, times the sum, the linear combination of the harmonic oscillator's energy spectrum, so the integrals of the constants of the harmonic oscillators, with this coefficient in front, the cosine. And let's see what we get from that. So we know that this is an adiabatic invariance. This has been proved by the work of Tamara Grava et al. And just to understand how these behave as an ergodicity indicator. So what happens now if the system reaches what is expected to reach the energy equipartition for a high value of energy? If all Ek are equal and they exit this sum of the cosines that run from 1 to n is identically equal to 0. So this is just an identity, so it must vanish. So this J hat is J minus 2 times epsilon, just to understand what exactly this sum does when we reach statistical equilibrium. And these variables, I want to mention, that's why I keep that they become uncorrelated variables. Okay, so the sum of them, of the product of 2 subsequent momenta, and the sum of all of them, as well as the relevant differences, must become uncorrelated and must tend to 0. So if the momenta themselves follow a Gaussian distribution, the sum of them should fluctuate around 0. And another information is that how they have, while the system behaves as a Toda, these 2 terms like counterbalance, so that give to J a constant value. When the system tends to reach equipartition, you see that these nice oscillations, which are quasi-periodic, start to become more irregular, and the system, they will vanish eventually. When the variables uncorrelate, they will tend to 0, and they will stay to 0 forever. And at this point, before we show some numerical results, I would like to to point out a nice indicator, a nice ergodicity indicator that was developed by Giorgio Parisi, the famous physicist in Italy. And so he calls delta T, that is the sum of this product of two subsequent momenta and normalized, so divided by Qn squared. Why this? Because it is reminiscent of this term. So it's really, okay, he considered the momenta of the positions, but the oscillations are not too far from each other. So it's really almost half of this sum. So just, and Paris indicates in this paper that has chosen this quantity for these reasons. It's an intensive quantity and can be measured with very high precision. When the system is unperturbed, okay, imagine that here alpha is equal to 0. It does not depend on time at all. And initially it starts from a value near 1, so a high value near 1, and then must be 0 in the Boltzmann-Kiels sample. Okay, but I didn't imagine when I read that paper that this might be slightly related to the Toda integral. So we'll contrast this in the numerical results with the Toda integral. These two expressions are the same essentially, okay, so I'm keeping them in that way just to indicate that this is in contrast with a Paris indicator that regards configuration variables, and the other one is in the normal mode space. This is the so-called spectral entropy, is the mostly widely used in the whole literature in order to find this critical energy and in order to determine the equilibrium times with precision. So this is the most famous indicator that one uses in the context of statistical mechanics. Okay, so let's show how they behave in this original experiment. So in the original experiment that we saw sometimes, a lot of times, the Toda integral along the FPUT dynamics is constant. So this shows also that it's an adiabatic invariant. The oscillations of the Toda integral along the FPUT dynamics is of the size of 10 to the minus 3 here. So it's really negligible compared to the how the energy spectra oscillate. The Paris indicator, has a size of about 10% of oscillation. So this, imagine that the Paris indicator is nearly the half size of the quadratic terms of the Toda integral. And so it's still a very good indicator. It really smooths out all these oscillations of the energy spectra. So it still does better. If we regard the spectral entropy, however, we see that the oscillations are 150% of the size of the energy spectral oscillation. So with that regard, it's better if we use the Paris indicator or the Toda integral instead of the spectral entropy, which fluctuates quite a lot. However, all the indicators display an integrable-like behavior. So if we plot these indicators, how they behave in time for this particular 32 particles original simulation, we see that J is constant. The quadratic terms and Paris indicator, of course, they do some fluctuations. Because especially this cosine approximation, the sum of the cosines times the energy spectra, just a quadratic approximation of J, so we expect it not to be perfect. And the spectral entropy has these large fluctuations. Now, this is about quasi-periodicity and adiabatic invariance. Now, what happens if we regard a high energy and we do observe the energy equipartition and the statistical equilibrium? So this is how the Toda integral would behave. It would be constant, so it would behave as an adiabatic invariant for some time, till this T0 time, and then it will depart from this value and reach the equilibrium value, which is 0. Okay, this is J hat, to be honest. It's like the sum of the linear combination of the energy spectra. While if you regard the spectral entropy, on the other hand, you see some different behavior. So you see a plateau that later on you see some oscillations and a tendency to a constant value. So there's no indication of this stability time. So so for this stability time, the system behaves as toda, and we have a clear indication of that. While in the spectral entropy, there is no such indication. Now, about equilibrium times, also here is a clear indication that here the system at this time has where it oscillates around 0. You have that it is at equilibrium. And while here, it's not really clear if it's here after 10 to the 5 or so it's a bit more accurate to regard the toda integral. And that is the point of the talk, that it's actually a very good indicator and very precise. So it's better if we use the theory of integrable systems and as indicators in all senses, as observables or as ergodicity indicators. So here, in this example, there is another point, that if we want to find this energy crossover, it means that we need to go to very high values, and that is very expensive numerically in terms of CPU time. The problem is that in spectral entropy, you have a double sum. So you have an extra factor n to find your equilibrium time. Instead, the idea that was used in the paper with Christos Efthymiopoulos is, instead of searching the equilibrium time, why don't we search for the stability time? So let's search for the time where the system behaves as toda, and we can cut here the numerical simulation. So we gain a factor about 100 in this particular case, and for 1,000 particles, if you stop here, because you have a single sum in J and a double sum here, you also gain a factor of n. So for a problem of 1,000 particles, you gain 10 to the 5, for example. So it's really more useful to proceed with the numerical simulations. And it's quite important because you have a very constant behavior. This is over the logarithm of time. Then you have departure, and then the reach of equilibrium. So it's a very clear indication. So we can call this the corrosive stability time, and the other one equilibration time, where the system reaches equipartition. And we can systematically search for this time only, this stability time in the corrosive sense. Now, we proceed with these numerical simulations, and we reach a high value of n, like 8,000 particles. And we regard not the excitation of the first normal mode, but much more general initial conditions as this one. So we regard random positions and random momenta extracted from a uniform distribution. And this is the behavior of J for different values of the energy. So if we regard, like, say, a value of the energy, this is 10 to the minus 1.75, we get this behavior. This is the stability time. This is for a lower energy, 10 to the minus 2, and so on. I think the last one is 10 to the minus 3. And we find this nice sigmoid curves. Now, with a rescaling time, we can find that they merge into 1. And why is that important? It means that we don't have to find equilibrium times. If we know how tau rescales with the energy, the tau is the rescaling time, so we merge them all together, means if we know this law, this power law, it's enough to evaluate only the stability time and say that we know then what will be, we can predict what will be the equilibrium time. And this is how it depends on the energy. And this slide is how it depends now on the number of particles. Apparently J is a very nice intensive quantity. That means it doesn't change with respect to n when the system is ergodic. So when we do have ergodicity, you see three values of the energy. So this 10 to the minus 2, this is 10 to the minus 3, for 8,000 particles, 1,000 particles and 200 particles, and they all coincide very well. Okay, so we do understand how the system behaves when it is ergodic, and we, by employing J, we know kind of everything about the system. And we can plot the stability time. So in this example here, for these three values, for example, this is minus 3, the energy, 10 to the minus 3, 10 to the minus 2.5, and 10 to the minus 2. So if we extend the computations for a range of energies, we find this nice power law. Okay, so we know how the stability time would depend on the energy, and that it is independent of n. So we would say that if we have a number, if, for example, we have an n value, let's say 1,000, 2,000, 10,000, or 100,000 particles, the stability time where the system stops being total and becomes ergodic should obey this line, this power law. But here, what we need is this energy crossover where the system is not ergodic and does not behave as an ergodic. So this intensive quantity is not always the case. Once we cross this energy crossover, so going to lower and lower energies, at some point we cross an energy crossover and we enter on the other side. So if we regard a lower value of particles in this example, like before it was 200, here there are 100, at some point this, you see, doesn't match very well. The stability time of 200 particles or higher was something like 10 to the 6, while the stability here is one order higher, is 10 to the 7. So you see the system starts prolonging its route to a copartition. So it starts to enter in some energy regime. So we mark exactly what is this energy crossover for 100 particles. Now, if we go to lower and lower n, like here it's 32 particles, the disagreement is quite bad. So for 10 to the minus 2 energy, this should be here. For 10 to the minus 2.5, this blue line should have been here. So you see it's a quite longer time. And for 10 to the minus 3, it doesn't seem to want to reach a copartition at all. It behaves as completely integrable. So for 32 particles, this crossover, which is 10 to the minus 3 for higher systems, for 32 particles, it is definitely higher to the 10 to the 10, with the maximum capacity that the computer could run. So in a nutshell, we can gather all this information together. So this graph with the power law about the stability times when the system is ergodic, it starts diverging and shows these exponential curves, which show that we enter in another regime where the stability times are longer and longer. They are exponentially long, exactly in the Nehoroshev sense. And this is an indication that we can find this energy crossover and how it depends on n. So the graph below is aiming to answer the problem. So exactly when it detaches from let's say that this is the ergodic indication, the dust blue line. So for 64 particles or 34 particles, we plotted this energy crossover. And the original FPU in initial condition is below that. So below that line, we have this nice weakly chaotic or quasi-integrable behavior. And above that, we have the strong indication of ergodicity. So this behaves as 10 to n to the minus 1.7. And in simple words, if we go back to this graph, where we said that theoretically was found this 1 over n to the power 6, this is the original FPU energy. And the numerical estimate of the previous graph finds that this is something like minus 1/-1.7, the logarithm of the critical energy. So that means that we really lack of some theory here to be able to justify why the boundary is so high, and to be able to justify what happens when n is quite higher than 32 particles. So I will close this talk here, and will say that the future plans how to tackle this problem is, first of all, we need to employ all Toda integrals as a set of observables. This mainly has been done only by the first non-trivial one, and then to proceed with the numerical simulations, since n, j, the Toda integrals, can do this work for pushing the n border to higher and higher values. And then finally, the main goal is to use perturbation theory to justify these numerical results. And there are some ideas how to tackle this problem. So thank you very much for attending this talk, and I'm happy to answer any questions.
Okay, thank you very much. So are there any questions? Okay, one question from the audience, 1 second.
I would like maybe make not a question, but two historical remarks. First of all, in the original paper, there were 3 different systems were considered, with cubic nonlinearity, with 4th order nonlinearity, and with piecewise quadratic nonlinearity, so piecewise linear force. And though the cubic model was one of the 3, considered the original paper by Fermi, Past, and Ulam. And maybe second remark, the integrability of the total lattice was independently shown by Flashka and Monakov.
Okay, thank you. Any more questions or remarks? Okay, no questions from the audience. Maybe questions.
No, I have a question.
Yeah, please, Tamara.
Hi, Elena. Many thanks for the nice talk. I would like to maybe, so the 10 to the minus 6 is a theorem, the threshold of epsilon 10 to the minus 6, this threshold that you gave. Yes, this epsilon critical minus 6, no, is a theorem.
Well, many different approaches and theories have proved that, yeah. I mean, I was thinking the paper of Sopoliansky mainly.
I see. Okay.
Yeah,
no, because please.
Yes, please.
No, I have but I'm not. My memory is not very good. But I have a more recent paper of Maspero and Bambuzi and Maspero, where, if I'm not wrong, they give 10 to the minus 4, something about minus 4. But so they say that if they take a packet of, but this actually is a different taste of result. They can show that if you take a localized packet of modes, it remains localized, something like that. But you need to be very low, like yes. Mm-hmm.
Do they? I think they find the same law, that 1 over n to the 4.
Fourth, yeah.
Yes.
Yeah.
It's true. Yeah, I think I remember having a discussion with Bambuzi and. Yeah, but this is for the alpha model as well, or it's for the beta?
I don't remember honestly. yeah. But so you're saying that there is a gap in between, and what you find numerically is this minus 1.75.
Yes.
But this is because you cannot push forward your numeric. I mean, because maybe if you went longer, you will see something, or equipartition or whatever, or it's because you believe really this is a deal. So there is in between something that is happening.
So I think that to find, I'm not sure what the Maspero and Bambuzi have employed, what type of perturbation theory they used there. I need to read that paper. However, I know that in the work of Sopoliansky, for example, they consider the harmonic frequencies, and that is the problem. That if you consider the harmonic frequencies, then you get what is 1 over n to the 4. Mm-hmm. Maybe you have to consider some other type of frequencies, and the idea I did not mention is why not to use the Toda frequencies, but we don't have an analytic form of that. So if we apply the same type of theory, like the Cherenkov criterion, but based on the total frequencies, I guess we should be able to get something like 1 over n squared. And that will improve a lot.
Yeah.
And just a question that, yeah, as the first comment that, yeah, in the original paper, there was a cubic and there was a fourth order. I did not mention at all the fourth order. First of all, the fourth order one system works better with the Cherenkov criterion, and no problem with that. The cubic one is the most mysterious one, and that is the related one with the KDV equation and the total system, not the fourth one, not the beta one.
Eleni, now let me ask. I have a question, just to conclude. In the end, you mentioned the strategies that have to be pursued in the future, but I'd like to understand on this slide, what is our purpose? Is to reach the minus 2.7 or the minus 6?
To reach the minus 1.75 by theoretical methods.
So it is the minus 1.75 we believe.
This is what I find with numerics.
That's what you find, yes. So the others are then quite far away estimates, huh? The minus 6.
The theoretical one is quite far away. Okay, it's not precise, but this is just to give a contrast. And the point is not actually about 32 particles, but the problem is about when going to higher and higher n values. Yes.
Yeah. And so you believe that, yeah, minus 1.75 is the best one we have today.
Well, this is what I've got with from these numerical results. Yeah, and if you consider also the original one, I don't think you can see any tendency towards equipartition. So this is the original experiment is still higher compared to the theoretical estimates.
Okay, any more questions or remarks?
Okay.
Okay, in which case, let's thank the speaker again. Thank you very much, Eleni.
Thank you very much.
If you could please just turn off your
I'll try my
sharing.
best.
So I don't know, Tamara, are you ready to start in principle?
Yeah, sure.
So,
I'm ready to start. Let's share.
So it's my pleasure to present the next plenary speaker. Is Tamara Gravra from the International School for Advanced Mathematics in Italy, and she will be talking about Soliton versus the gas. So Tamara, I apologize in advance because we can see you on the big screen, but you cannot see us. So,
yeah, indeed, but it's fine. I mean,
so you can start whenever you're ready.
I don't know what you see. Is a slideshow or not yet? I mean, this is not a slideshow. Sorry.
So we can see perfectly your screen.
Okay. So I can start.
Yeah. Yes. Whenever you're ready.
So thank you very much, Sotiris, for organizing all this. It's a great event. So what I'm going to talk today is about a joint work. There are two joint work, one with Manuela Girotti from St. Mary University, Bob Jenkins for Florida, and Ken McLaughlin, and this is a base, the first work is based on a CMP paper in 2020, and then there is a recent preprint where also Alexander Minakov joined us. Okay, so this is just, it's a paper, these two papers are basically studying KDV and modified KDV equations. So we are in the PD setting where there are infinite number of solitons. And the idea is to understand a little bit the dynamic of this infinite number of solitons. Okay, so solitons, why we are doing this? Because solitons are fundamental solution of integrable equation. So when you have a lot of soliton, despite, the dynamic of one soliton is very simple, when you have a lot of soliton, things become very complicated. So let me first study, the simplest, okay, one soliton solution, there is not much to say, but when you have two soliton, there is a little bit more to say. And so you have a slow and a faster soliton. When the faster soliton takes the slow soliton, which this is, I mean, it's not still, but it moves a little bit. So there is what happened is just a phase shift. Everything remained the same. These are solitons interact like particle, I mean, like that scatters without changing their shape. And the effect that you have is only a phase shift. And just to show what it is, so well, in this plot we have the soliton. Here is the soliton position. So this line here, can you see my mouse?
Yes.
Okay, this is the soliton position. This is the soliton velocity. So when it interacts with a small soliton, so there is a change, you can see. And this is the soliton acceleration. Okay, so this is the setting, and it's a very standard from the theory of integrable system. This is shown for the, so what I'm talking about here is the modified KdV equation. So we are in one space dimension, X is on the real line, and Q is a real variable. So, and this plot here is the soliton solution. Okay, so the interaction of these two solitons, so I will say that the soliton, when they interact, I mean, the faster soliton have a kind of acceleration. And so what you perceive, and then it keeps the same shape. What you see on the effect of it is that if you prepare to soliton at minus infinity with two different speed, and here eta 2 is bigger than eta 1, so this is the Setch, so the soliton solution. This is for KdV actually, not for modified. So this is at minus infinity. What you see at plus infinity is the same shape. So we have the same soliton, and the effect of this phase shift is given by an explicit formula which has this logarithmic term. So the shift is bigger if eta 2 minus eta 1 is bigger. Okay, so this is very standard. And then there was an idea of a very old paper of Zakharov that is date 1973. Okay, so suppose now that we have what we call a diluted gas of solitons. We have a lot of solitons, and we give a concept of soliton density, which means is the number of this is the density of soliton which are at position x in space, t in time, and with spectra, so the spectral parameter eta, which describes the soliton velocity. And so if you put here the eta, the x, and the t, this is the number of soliton that you see in the interval. So, and then we launch a bigger soliton, what it calls a tracer soliton. And then the question is, if I look at one specific soliton and I want to see how its velocity is modified by the interaction with all these soliton, it cook up this equation, which is an integral equation. And S is the velocity of the soliton, is equal to, sorry, maybe I should have gone back. So is equal to his velocity with a free soliton plus a correction term, okay? And this correction terms, so is as a logarithmic term, which just to go back, so is kind of coming from this logarithmic term here. So this is the soliton velocity for eta squared. So
Tamara, sorry for interrupting. I was wondering if you could make it a full screen. The thing is, to us it's visible, but on YouTube it streams a little bit small.
Yes, I thought I was doing full screen, but so let me slide view full screen, enter full screen. And this is what is showing.
Okay, it's full screen already.
No, sorry, but why is like that? Keynote view, so full screen. Zoom.
For us?
I took customer play.
Yeah, no, I think for us.
Play slideshow. Maybe let's try this one. Yeah.
Yeah, that's great. Thank you very much.
Okay.
Sorry for interrupting.
Thank you. Okay. So, so this is, just to come back, so the soliton, but now, where is my mouse? Sorry. No, I don't see my mouse. The only problem is I don't see anything.
Yeah, I guess full screen doesn't show the mouse, so okay, maybe if you want to show, then put it back to the previous mode if you want to show questions.
Sorry, just 1 second, that maybe I'm trying to put this annotate with, okay. Okay, and so now let's go back. View, where is it? Played slide. Okay.
Yeah, now we can see it, yeah.
Yes, sorry for... Okay, so what I want to say here, yes, we have the Soliton speed that is 4 eta 1 square, that is so the point spectrum of the Soliton plus this interaction. So when you go back and you come to this equation here, so you have the velocity of the Soliton is equal to this to his velocity as a free Soliton plus these interaction terms. And here is the Soliton density, and we are integrating between 0 and infinity, which is taking track of all Soliton present. So you want the Soliton density to be a rapidly decreasing function, so you don't want to explode at infinity, so that everything here is convergent. And then there is also a consistency condition for F, for the Soliton density, that is given by this conservation law. I just want to remark that usually when you write a conservation law, this is the speed. So it's the speed of or the density of your object, and satisfy so it's given by this equation. Okay, so this is a non-standard. So if you think of a density of Soliton or a Soliton gas, you have this conservation equation plus this velocity term. Okay. This equation were, as I said, obtained by Zakharov, and then later Gennady L was able to derive, and were obtained by Zakharov, I want to say, were a very dilute Soliton gas. And L extracted the equation of this equation for a dense Soliton gas by taking the limit of finite gap solution when your number of so a G gap solution when the number G goes to infinity, so the G will explode, but on the other side you have a solitonic limit, so the size of the gaps becomes smaller and smaller. And this was extended in several directions by many authors here. Maybe I'm not putting all of them, but it was extended by L and Kamchatkov, by Tobis and L, Pelinovsky, Shvigalina. So there are many people who contribute to this field. But what I want to say is that this integral equation, now you have this velocity, Soliton velocity here, and the Soliton velocity here. Okay, so no, again, I don't know what sorry, I don't see anything, sorry, again. So, okay. Okay, so the point of this talk is so are these equations, so the point I want to try to understand is, are these equations obtained, so this kinetic equation for Soliton obtained and when there is randomness, or can we get this equation for the Soliton in a Soliton gas also in something more regular? And when we have a deterministic infinite set of Soliton, this is the goal of my talk. So with randomness, so this is the idea of randomness, was of course introduced by Zakharov, and the idea that this F in the equation contains a Soliton distribution. But what I'm going to talk now is instead I consider an ensemble of infinite number of Soliton when this infinite number is deterministic, so I give a Soliton density that is given. And so the idea of getting infinite number of Soliton was already developed, actually, already came out in the study of the small dispersion limit of KdV in the work of Lux and Levermore. So if you consider the KdV equation with a small parameter in front of the dispersion, and you take initial data that are where for this sign of the equations that are negative, so and they have only solitonic components, when epsilon goes to 0, the number of soliton goes to infinity, because you are getting an infinite number of point spectrum that accumulates in an interval. And we can consider also, in this sense, this limit a preparation of a gas of soliton. So that should lead at least in the same way as the Galois idea should lead to a sort of kinetic equation. Okay, so now let me start. Sorry, I'm a little bit okay. So my spotlight. Let's look. I cannot. Sorry, I have too many things that I don't like to see on my screen. So. Okay, so now let me describe the initial value problem of the KDV or the modified KDV equation that I'm going to speak about. So these are integrable equations, and they can be solved via an inverse problem. And so the construction of the initial value problem is as follows. So for both equations, so on one side we have a modified KDV equation, on the other side I have the KDV equation. The construction is similar. And so the goal, the integrability of both equations was obtained through a Lax pair. In this case, it's a scalar equation for KDV, and is the compatibility. So we have the Schrödinger equation, and then the time evolution for the eigenfunction on this side. So since we are considering focusing, so this is a non-self-adjoint Lax operator linear equation, and the time evolution is given by this expression. The inverse problem can be formulated. So we do inverse scattering. So the inverse problem can be formulated as a Riemann-Hilbert problem. And this is the following. So don't be scared. So this is for KDV. So you want to find, and I'm only giving you the soliton Riemann-Hilbert problem. So we want to find in the complex plane lambda, so the lambda is the spectral plane where the spectrum of the Schrödinger operator takes place. So we want to find a vector function M, which is meromorphic and has only simple pole, lambda j, and this is R complex. And the condition is that, so you have a meromorphic function, it satisfies this residue condition. And here the data, the input data are these constants, Cj, that is the norming constant of the soliton, and the position, so the spectrum, which gives the velocity of the soliton. We have two conditions at lambda and the complex conjugate. And then we need to fix the solution uniquely. We need the condition at infinity and some symmetry. So once you have this data, the KDV solution, so the n soliton solution is solved just by taking the one entry at infinity of this matrix. So this is solved in terms of rational function and gives the usual determinant formula of the n soliton solution. And similarly for the modified KDV, so in this case, we don't have a vector problem at a matrix, and becomes a 2 by 2 matrix. The situation is the same. So you have poles that live on the complex plane. Now the kappa j are real, and this is the norming constant. And this phase here is very similar to KDV. Now we have a matrix, so the condition of unicity of the solution is to have this matrix that goes to identity plus small terms as kappas go to infinity. And as for the KDV, in this case, the 2-1 entry is the n soliton solution of the modified KDV equation. Okay, so this is the setting. So you have to think of this to having a finite number of kappa j on the imaginary axis, and I take a norming constant kj. I divide by n now because I want to send n to infinity. Understand what is this problem looking. Okay, so we have, as I said, this case, and I have a finite number of pole here. So if we want to send n to infinity and try to see what happens, so we can think of kj as a discretization of a smooth function, which I call rj. So I take a, sorry, R, I take a smooth function R, I evaluate a kappa J, and this is called my Tj, which are the norming constant of my, of the solitons, okay? So the limit is to think of these dots here on the imaginary axis, which are the points of the soliton spectrum going to infinity. So we want to send the number of soliton to infinity in a finite interval on the complex spectral plane. So, and this originally, so the motivation for this originally came from a work of KASCHENKO, Zakharov, and Zakharov, who found a new kind of solution of KDV. And as a particular case of their solution, a particular case of this class of solution found by Zakharov are exactly the solutions that are obtained as a number of soliton goes to infinity. And so when you do the gymnastic of sending the number of soliton goes to infinity, we arrive at this Riemann-Hilbert problem. And this is for modified KDV. So you want to find a matrix function 2 by 2 X, which is analytic on the whole complex plane, goes to identity at infinity, and has this jump condition on the imaginary axis. So this is the position where the soliton accumulates, so accumulates between eta 1 and eta 2, and the same here. So this is symmetric. And the density, the soliton density, I mean, the norming constant, I mean, are interpolated by a smooth function or continuous function are okay. So this is the setting. So coming back, I am starting with something finite and a residue condition. And when you do some gymnastic with this problem, so this is, so I want to say this problem is solvable in terms of rational function, elementary function, and the solution is given in terms of determinant. When I send n to infinity, I mean, you arrive to this kind of problem, and you want to study the solution and the behavior of the solution, okay? So this is the setting. And the behaviors of the solution for a long time. So this is, I want to send t to infinity, understand how the solution of this initial value problem behave. And the claim is that this is a really soliton gas. So this is this kind of initial value problem really behaves as a soliton gas. So this is a plot for KDV and is the solution for a long time. So coming back, so the solution of this initial value problem at time t equals 0 is characterized at minus infinity by oscillatory waves. So it's a step-like oscillatory data, step-like, which oscillate at minus infinity and is going to 0 exponentially fast at plus infinity. So this is the characterization of the initial data. And in between, we don't know what it is. But at minus infinity is oscillatory, and this is the oscillation. At plus infinity is 0. And then this is the time evolution. So the time evolution is given clearly a dispersive shock wave, because it's a step-like data, and so the evolution, this is for t goes to infinity, so for large time, so we have the oscillation that comes from minus infinity, and this is the modulated wave, dispersive shock wave, and this is 0, which is the solution, which is exponentially small. Just I want to say some comment. So the fact that we have oscillation at minus infinity and data that is 0 at a plus infinity depends on the sign of this exponent. So if we change the sign, we will flip the situation. We will have oscillation at plus infinity and 0 at minus infinity, and the solution will be a rarefaction wave. So we choose the sign of the exponent so that to have a dispersive shock wave. And okay, so this is the setting. And now to study all this, you need to introduce what is usually called the G function to do asymptotic on the Riemann-Hilbert problem. And this G function is defined as the integral of a log of this quantity, which resembles very much the kernel of the soliton interaction, plus a quantity, a density, which I call rho, and is determined by this integral equation. Okay, so this is what happens when we study our soliton gas, or density of soliton. And almost an observation is that this if I take this density, that is the solution of this integral equation, and I take the ratio rho t over rho x, so this is a function of x and t, and I call this v, this is satisfy the kinetic equation of L Zakharov. Okay, so basically I want to say that for a Soliton density f that I'm not going to speak about now, but this is almost out, is almost a tautology. Satisfies, so this v, that is the ratio of I will say this is the wave number, and this, sorry, this the frequency, and this is the wave number of the Soliton gas, satisfied Zakharov kinetic equation. Okay, so now let me change setting. So I want to consider the same setting as before. And this is, so we take this Riemann-Hilbert problem, which has a jump on the imaginary axis with some density R of k, and I add a bigger soliton. And the goal now is to understand how this soliton is behaving. So this is, so we add a bigger soliton, and this bigger soliton is determined by this residue condition, as we usually determine solitons. So as again, when you solve this Riemann-Hilbert problem, the solution of KdV or modified KdV, in this case we are talking about modified KdV, is given by the behavior at infinity of the function x. Okay, so and here is the goal is to understand how the bigger soliton is behaving on this background. Okay, and to show that we indeed have again Zakharov kinetic equation. So just to show the picture, this is a little bit slow. Okay, let's try to speed it up. So this is a bigger soliton which interacts on the background. The background here is the soliton gas that looks quite regular for the parameter taken, but is a modulated soliton. So this is not is not an exact solution of modified KdV. You see there is modulation. We have a refraction wave. And so here we have a modulated rarefaction wave. Here we have an elliptic wave. Now we have the initial data is to have oscillation at plus infinity and 0 minus infinity. And we have the soliton which interacts with the soliton gas. So the goal is to give a description of the velocity of the soliton in this soliton gas, and to check whether this velocity is indeed a solution of Zakharov kinetic equation, and the answer is positive. So this is just a picture of a snapshot of what you just saw. So here we start with the big soliton interacting with the soliton gas. And the gray here is the position of the peak, so during the evolution. And we have 4 snapshots. So the red line here is the position of the soliton if it was traveling with no interaction. So it's the free soliton. The fact that we have interaction makes the soliton looking faster, so like move faster, and this is the effect of the phase shift. And so, and here is the position of the soliton. Okay, so it's oscillate, and the oscillation are given by the fact that it is interact with this soliton gas. Just to be precise, yes. So if we take the soliton which is not big enough, and this is an example, so we are in the same situation as before, but the soliton is not big enough. So there is okay, when it starts to interact, we have okay, we can still distinguish the soliton. So to say that the highest peak is the soliton, but at a certain point we have peaks of the same amplitude, and so we are not able to see which is the maximum, and so we are not able here to identify which is the soliton. So in our analytical description of the problem, we need to have a unique single maximum, and so for this reason, we need to take the trace of the big soliton sufficiently big that this condition is not taking place. So the soliton should always be big enough that we don't have 2 peaks that are of the same amplitude. Okay. So the analysis. So we want to solve
Tamara, excuse me, just to understand. By soliton gas, therefore, you mean a periodic arrangement of soliton?
No, it's not a periodic arrangement, it's not a periodic arrangement.
It looks very periodic.
Yeah, that's the fact. That's the fact.
But they're not running with the same speed, you mean? Huh? They're
asymptotically, yes, but it's not exact. It's one of asymptotic. So maybe let me precise. So what I'm showing here is actually is not. Yes. So thank you for interrupting. So what I'm showing here is not the solution. Okay, it's not the solution of this problem because I'm not able to do it, but it's the asymptotic solution that at leading order look like a modulated periodic wave at leading order.
Okay.
Okay, I'm showing the asymptotic solution that I get analytically.
Okay.
The plot here is the asymptotic solution, but not the true solution of the problem.
The asymptotic solution. Okay, fine.
The asymptotic because it's the only one I'm able to plot.
Yeah. I understand. Right.
Yeah. Thank you. But it's modulated. So it's modulated. So this is at leading order, the leading order solution of that problem for large time. Leading order. Okay. So as Sugantis was asking me, so now let me explain very briefly the analysis. I'm not going to speak much about this, but so we want to analyze the Cauchy problem I show you above. So this Riemann-Hilbert problem for this function x as t goes to infinity, and several ingredients are needed. First, this g function that I already introduced. Then this c that is just g plus the phase, so this 4t k squared plus x, and then there is a change of variable. So we introduce a new matrix T, and with this new matrix T, we introduce another matrix S. And and this F is unknown, and this rho is unknown, but are determined by some further condition. But the whole goal here is to reduce the original jump matrix on this interval eta 1, eta 2, so eta 1, eta 2, to reduce them to something simpler that we are able to handle and to solve. That's so you deform contour in such a way that the term becomes exponentially small or exponentially large, and then you can do transformation to kill them. This is the whole goal, and you remain to something which is simple, like these original jump here are turned into constant 0, I 0, and the same here, and this is become diagonal. So you do a certain number of transformation, and in such a way that your exponent here that were oscillatory, the original exponent are all oscillatory in the imaginary axis, you move things around in such a way that become exponentially small or exponentially big, and you can kill them. That's the whole gymnastic. And so this is the transformation. And regarding the function S, and then the soliton, the bigger soliton. So we have a bigger soliton out here. So the bigger soliton condition, so the residue condition of the soliton with all these changes is only affected that we introduce a function f. So the original norming constant is affected by only this function. So it means that it gives an effect of shifted the soliton. So when we do this analysis, the original soliton with norming constant chi is multiplied by this quantity, which depends on space and time, but this is okay, and is making an effect of shifting things. Okay. So as I just said, in all this analysis, the intuition is that we should get rid of large, exponentially large and exponentially small thing, and try to isolate the relevant terms on this Riemann-Hilbert problem. And so the soliton peak, and that's why we need one peak only. So the soliton speed is determined by calculating this phase function here at kappa 0 and saying this constant. And extracting this quantity, so this quantity gives that the average soliton velocity, actually, the average soliton velocity is equal to the derivative with respect to time and x duration, and so is equal to this quantity. So here I forgot the term of 1 over plus 1 over t. But so is the original soliton for kappa 0, so we are in modified KdV, plus a correction terms that comes in terms of elliptic integrals, and plus the background velocity. So this is the velocity of the elliptic integral, of the elliptic function that is interacting with. And then there is a correction term that is 1 over t. And so again, with all this analysis, let me say only one theorem. So the analysis say that this Riemann-Hilbert problem and this inverse problem gives for when we are in the Soliton region. So we are looking in a direction x over t, which is bigger than 4 eta 1 square. So we enter the oscillatory region of the background is equal to the background plus a Soliton plus terms of order 1 over t. And the background is describes in terms of elliptic function. So the n is the standard Jacobian elliptic function, and this quantity here is 0, 1, and 2 are usually constant for exact solution, while in this case are weakly dependent on x and t. And then we have 1 over t correction. And the Q Soliton is a very complicated expression in terms of elliptic function, but the only thing we can verify is that for kappa, and the Soliton is very big, so it's much bigger than the background. This tends to the exact Soliton, so we arrive at the Soliton. But otherwise, it's a very complicated expression in terms of elliptic function. So it's I'm not showing it. Okay, coming back to the Soliton. So what so we have this average Soliton velocity, and it satisfies the Zakharov-L kinetic equation. So this is satisfied the Zakharov-L kinetic equation. And here, so this quantity is a group velocity, which is given by phi t over phi x, this quantity here, and this is the density which is contained in the function phi. And so regarding so this is we call it the average velocity, but the true velocity of the Soliton, what it is. So we calculate it, and to calculate the true velocity, we have to identify the peak, and that's why we need only one maximum. So you need only one maximum. So in the asymptotic analysis, I can follow the peak, and I can say that there is a time for which the peak is given by the free Soliton, and then after a time t1, it solves this differential equation here. So this dot is the velocity of the Soliton is equal phi 2 over phi 0. Sorry, this psi 2 is phi t, and phi 0 is phi x. So it's derivative with respect to time and derivative with respect to space, plus these terms here that are expressed in terms of elliptic function. And then there is a terms of order 1 over t. And the initial condition is that t1 should be equal to x1 when you plug it here. So the remarkable, so this is the true Soliton velocity that come out from the asymptotic analysis of that Riemann-Hilbert problem. And the remarkable thing is that if I look at the peak velocity and I average over a period in time, so this is the velocity average over a period, this is come out to be really equal to the average velocity that I was given here, and which satisfy Zakharov kinetic equation. So the message here is that, okay, so this big Soliton interacting with this Soliton gas as an oscillatory velocity, clearly, because it's oscillating, but its average velocity satisfy modulus terms of order O of 1 over t, satisfy the Zakharov kinetic equation. And okay, so maybe I went too fast, I don't know. Okay, so this is just to see. So this is the Soliton velocity that you don't see it very well, but when, so this is the Soliton peak position, and now I'm subtracting the location of the vacuum, otherwise you don't appreciate very much the behavior. So the position of the Soliton is having as this step-like behavior. So it's because it's moving, and so there is this step, and this is the Soliton speed. So the soliton speed is highly, so here is entering the rarefaction wave, so it's increased, and then this is the soliton gas when it's approximated by elliptic function. So this is the soliton speed that you can see is highly oscillatory, and the black line here is the average velocity. And so with x dot peak is exactly this oscillatory behavior, and when we average over one period, so we average over a period here between two oscillations, you get what is this average velocity VW sol that solves Sakharov kinetic equation. And if we want to see the position of the soliton over the soliton gas, this is many pictures appear in the literature. But so this is the velocity of the soliton as it were with no interaction. This is the deviation due to interaction. Okay, so I think I said almost all I want to say. That basically the message is that when we consider a gas of soliton and then we take a bigger soliton, then it behaves indeed as so its velocity satisfies Sakharov L kinetic equation, so so everything here is deterministic. So and the message is so it has the soliton behavior. I mean, it satisfies, I want to say, the Sakharov kinetic equation, and it has the same feature as a soliton gas in the presence of randomness. But this is an explicit deterministic solution. So so it's not clear why this equation holds, and maybe it's because there is concentration of measure, or because other things, but the message is, okay, so we have an example of deterministic soliton gas, and where the behavior of soliton are still in the setting of this Sakharov kinetic equation. Okay, so I think that's all I want to say. Probably I went a little bit fast.
Okay, thank you very much. Are there any questions or comments?
I raised my hand.
Yes, sorry, yeah, I was looking on that and sorry I didn't notice. Yes, please.
Okay, if someone else is right. When Fiuma is okay. My question, Amara, is it's very interesting talk. I wasn't aware of all these developments, and the question that comes to my mind with this soliton gas is that it must have been experimentally observed somehow.
Yeah, this also, this oscillation, there is a group in Boulder, Colorado that they really saw this oscillation. It has been observed very recently. I'm sorry to not have mentioned it.
But on what?
I think on
water waves. Water waves, maybe.
I think in water waves, yes. I mean, I think.
Because it must occur. Does it occur also in the nonlinear Schrödinger equation?
It occurs also in nonlinear Schrödinger equation. I mean, modified KDV is very. I mean, okay, it's the real version of NLS, but it should be the same.
But NLS is different, and it must be also viewed in terms of little optical pulses.
Yeah.
If it's this should have been observed maybe experimentally in many pulses at the end.
Yes, in optics, I don't know. I mean, I will meet, there is a conference in Cambridge on this field, so maybe next in 1 week starting a program. So I will meet people and ask more detail. But I've been told that I don't know the people, but when Ken McLaughlin did this talk last month in some meeting in the US, he was approached by some experimental people, and he was told that they did experiment on this, and they saw exactly all the oscillation we are seeing.
Okay, an interaction with a single wave, maybe also.
Yeah, they put a lot of soliton plus a big soliton, and they see exactly.
Okay, thank you.
Okay, I see one more question by Wenzuma. Sorry if I mispronounce your name.
That's right, good actually. Hello, I'm Wenzuma.
Nice to meet you.
Hi, Tamara. Yeah, yes, good actually. We have some connection before anyway, through the email. I think about publication sort of things. Anyway, I have Soliton gas pretty new anyway. I'm very interested in that, of course. But anyway, I have a few questions. But one question I want to ask here is, so the Soliton gas is actually pretty generalized class of the solutions, right? Generalized Soliton.
Sorry, say it again, Dave.
I mean, the Soliton, the gas Soliton actually is a pretty generalized class of solution, KDV, which are modified KDV. I mean, with some kind of non-zero reflection coefficients, right? And my question is, can we see the pattern approximate effect there? For example, you know, the KDV has a rational solution, so we want to use the rational solution to approximate the solution to the Cauchy problem, whatever Cauchy actually just decay, okay, or L2 Cauchy initial. So what kind of effect you can say from the Soliton case? But the Soliton case is some kind of other kind of solution actually, more general, much more general than Soliton. So
yeah, and in this case we can say so only. I mean, so there are many open problems that maybe I should mention. Okay, so this is the Riemann-Hilbert problem. No, we send a number. So we send a number of Soliton here go to infinity. We arrive to this problem. So what we see at t equals 0 is depends on the sign of this exponent. You see an elliptic wave minus infinity, 0 plus infinity, and so this is what you see. In between, there was some simulation of in the paper of Dyachenko, Zakharov for this kind of problem. I mean, a little bit more general setting. But what I want to say, we are not still able to put Soliton both at plus infinity and minus infinity. So we are able to have polarity only in one direction. So we are not able to mix, so to see everywhere in the plane. So this is, but the expected, in this case, the expected is step-like. So the only thing I can say is step-like initial data with oscillatory behavior at minus infinity and 0 plus infinity or vice versa. When we mix the two, when we put Soliton both at plus infinity and minus infinity, I don't know what it is. So if I'm answering your question.
That's pretty helpful anyway. But anyway, no, yeah, my other question actually, you know, this is, I mean, modified KDV is simply the case, right? In the integrable system, of course, just scalar. Because we can actually, even the scalar integrable modified KDV, we have 3 by 3 eigenvalue problem. So we have third eigenvalue problem to describe the new integrable system, new integrable modified. I mean, the modified KDV question, you consider it just simply the case. But anyway, so if you consider other, my question is, is there any study on the 3 by 3 metric spectral problem or eigenvalue or limit problem, which we still can exploit the asymptotic of the.
No, I don't. I mean, probably yes. I mean, I didn't do, but I'm doing with a student now the focusing NLS, and it's very interesting because I mean, as there are recent paper by Lenel, Shepelsky, and Almuted Monvel, where they show that for step-like initial data in NLS, you are even genus 3 solution, so elliptic. So
this is about genus, you know, but eigenvalue problem. If you have the third order ODE, you know,
yes,
Sasa type modified.
Oh yeah, sure. I mean, you can do as complicated as you want, but I don't think it's been explored. Yeah. Yeah, I don't know what it is, but already for me, already in this case was quite was quite unexpected to see this this behavior. Yeah.
Good. Yeah. Good. And I have another minor question about your, because you show us the Riemann-Hilbert problem for the Soliton case, right? So, do you have the exact solution to this Riemann-Hilbert problem? Can you solve it?
No, it's asymptotic. The theorem is asymptotic analysis. No, it doesn't have an exact.
We just explore asymptotic, okay, based on the Riemann-Hilbert problem.
I am afraid on the determinant formula, but so.
Yes, you can present, of course, right? The
Soliton. So for this Riemann-Hilbert problem, there is a Fresnel determinant formula as with a kernel. Actually, the kernel of the Fresnel determinant solution has appeared in the work of Tracy and Whedon.
Right.
So it's a kernel that now is appearing in probability, actually. Yeah.
Right, because you use the distribution of the Soliton set. Yeah, definitely.
Yeah, but if you're asking, I can solve this problem in terms of Fresnel determinant. Yeah. So exact solution in terms of friend of determinant, but then you have a friend of determinant. Yeah.
Thank you. Thank you very much. Yeah.
Okay, any more questions or remarks? Okay, in which case, thanks again, Tamara, very much for an interesting talk.
Thank you for the invitation. Yeah.
So just a small announcement. So today we have a little change in the schedule today and tomorrow. So the talk by Professor Griniewicz will not take place today, will take place tomorrow morning. So we have a break until 2:30. So yeah, so we meet at 2:30 here again. Thank you.
Is Alexey Slunyaev from Institute of Applied Physics and National Research University High School of Economics.
Okay, thank you. And first I would like to express my gratitude to the organizers for the opportunity, for possibility to talk here today in this marvelous building. I'm really impressed by all this surrounding. My talk will be probably much different from previous talks. It will be about rather application of the theory of the inverse scattering technique to the real problems which appear in oceanography. And my first part will be more maybe illustrative, that it will actually my focus of my interest, there are events in the open ocean which are recorded here by this time series of surface, maybe like this. This is a surface displacement which is recorded as a function of time, and there are probably the first reliable records of what is called today rogue waves or freak waves, or in Russian killer waves. And you can see here that these waves, which are here located in the middle of these records, are much higher than all these surrounding waves. And this time series, they impressed much the oceanographers of that time. It was probably the beginning of 90s of the last century when this story started. And people wanted to understand the nature of these records and to understand are they really described by the present day formulas which are used in the industry. And today, just about definition, that first when people deal with surface waves, the common characteristic which actually characterizes, measures the intensity of waves, it is not amplitude but wave height, which is the distance from the lowest point of the wave to the highest point of individual wave, so it is h height. And another quantity hs, which is significant wave height. In statistical, from statistical point of view, it is about 4 times standard deviation for this surface displacement. So, and the most conventional definition of rogue waves, they are such waves which have heights at least twice higher than significant wave height. So, and here is one of examples of these freak waves or rogue waves, which was measured in the North Sea, 1st of January in 1995. Therefore, it is called New Year wave. So, and actually we started to deal with this work, with this problem rather far, and this is a cover of our monography, which is dedicated to this problem and published already more than 10 years ago. So, and well, people, people who are working with ocean waves, they are rather so we want to follow standard approach to consider waves on the sea surface as a result of the Gaussian random process. And then, so you just can develop this rigorously theory and obtain this formula for the probability of, this is exceedance probability of wave heights. So it's a probability to measure wave which is higher than the given height h. And you can see that it is an extremely simple formula. It's very beautiful formula that it takes into account, it has only one ratio h over hs, and again hs is about 4 times standard deviation. So it's exponential dependence, and on this plot it is given by the green curve. The horizontal axis corresponds to h over hs, and so this area of this curve, which corresponds to relatively low waves in amplitude and relatively frequent events, it can be just verified in experimentally, for example, in the ocean. And just to see, to compare this theoretical prediction, there is another line which is given by red and blue. This is the direct numerical simulation. And you can see that in this area where you can confirm, when we can verify the theory by measurements, there is good agreement, but there is already some disagreement here. And the problem is, the question is, how the reality corresponds to the theory, and if the reality doesn't correspond to the theory, what should be the proper theoretical dependence for this probability. This area cannot be just measured in the ocean because it is very rare events. And you could already see that the actual standards in marine industry, they actually require the knowledge about this curve, the true shape of this curve, for events which are 3 orders of magnitudes less frequent than given in this figure. And for example, if you here see that the difference between direct numerical simulation and measurements is about 1 order, you can just imagine how large the difference can be if we are considering even less frequent events. So therefore, since we cannot measure it in the ocean, so people try to answer the question about the true curve for this probability distribution theoretically or just by some maybe numerical simulations. And the first idea, which comes from the theory, what can be the reason of the difference from the Rayleigh distribution, from the Gaussian statistics, it is that we can have coherent patterns due to the effect of nonlinearity, which can change the probability distribution function. So, and fortunately for us, there are 2 integrable equations, nonlinear equation and KDV equation, which are the first approximations to water waves. KDV describe in the first approximation waves on the shallow water, and nonlinear equation, it can describe modulations of waves in deep water and also in shallow water, but I will talk about only the case of deep water. Then the nonlinear equation has the focusing type, and then we can have coherent structures in the form of bright or envelope solitons. So, and so why I said that we are happy or lucky that these equations can be solved by means of the inverse scattering technique, and potentially this gives us the possibility to change the paradigm of a spectral description, which is now the dominant idea in the oceanography, to change it to the so-called nonlinear spectrum, so to take to make use of this inverse scattering transform and the associated scattering problem and its eigen spectrum. So this is not really a very new idea. Here is this is a list of attempts of application of the theory of the inverse scattering technique to real physical problem in hydrodynamics. It is probably starting from 1991, and there are different pieces of attempts, and they try to do it dealing with KDV equation and also nonlinear equation. My first work, significant work on this topic, appeared in 2006, and I will not talk much about these details. So we try to use this technique, this idea, to find the keys to describe the rogue wave phenomena. So first, this is the nonlinear equation, now written not in dimensionless form, but it is dimensional form. It describes modulations of waves in deep water. The surface displacement is related with, sorry, it should be A here, with this complex amplitude using the wave number of the carrier wave and frequency of the carrier wave. So it is important that to write down the nonlinear equation, we should choose somehow K0 and omega naught. Well, and also we'll talk about it, that to derive this equation from hydrodynamic equations, we need the assumptions of small linearity in terms of steepness and narrow bandwidth of the spectrum. So the what is called Benjamin Fair index or Ursel number for deep water waves, or Soliton number or similarity parameter, this is just a ratio of this non-linear part versus dispersion part, or in terms of parameters, this is mean steepness over bandwidth, and it is expressed in this this quantity Benjamin Fair index. Epsilon, it is just the steepness, K0 all multiplied by characteristic amplitude of the surface displacement, and NT and NX, they are number of waves in a group in time series and space series. So they are related between each other with a factor of 2, because group velocity of waves in deep water is twice smaller than phase velocity. So it is very well known that if this index of Benjamin Fair index is larger than 1, then waves are unstable with respect to lone perturbations. In other words, modulations result in generation of envelope solitons. And just about real C, if we take this steepness, then the number of waves in one group in a time series should be about 10. But the parameters of envelope solitons are related to such way that twice higher envelope will be twice shorter. So therefore, for steeper waves, we should have shorter wave groups. So it was a theoretical idea, and indeed this idea was supported in direct numerical simulations and also in laboratory simulations. If we increase BFI, Benjamin Fair index, then the probability distribution indeed produces heavier tails in this. And it means that higher probability of very, very high waves. But unfortunately, so far, this idea is not successfully applied in the real ocean, in the forecast systems. However, there are attempts to do so. So let's consider numerical simulations. This is a result of our numerical simulations. We produce this distribution function, probability distribution function for waves using the direct numerical simulations of the full potential equations for water waves. And we make averaging over many simulations. And just so in this curve, there is a difference that the horizontal axis, it is h over hs squared. And then the Rayleigh distribution is just this diagonal line. And you see that we averaged over many realizations curve. We are indeed above this line. It gives us information that indeed waves with higher amplitude generated for, if you are interested in waves which are much higher than significant wave height. And I want to draw your attention that there are some realizations where the distribution is much above this averaged value. For example, this is simulation number 295. Let's consider what is peculiarity of this simulation. So this is a spectrum by red. This is the actual spectrum in this simulation. By black, which is the spectrum we wanted to simulate. They agree well, and no much peculiarities in the time series and space series taken from this simulation. But if we draw the surface which we simulate in this numerical experiment, this is time and this is space in comoving system of references. You can see, so this is time equal to 0, and then waves start to evolve. You can see that there is a huge group which is generated just occasionally from the initial conditions. And in fact, these groups, it results in this strong deviation from the distribution, from the probability distribution. So first idea, it is that very similar to Soliton-like wave group. So can it be really a Soliton? So we tried to answer this question just by applying the inverse scattering technique, or better to say solving direct scattering problem. But there are many difficulties when we try to apply it to the real ocean waves or simulated waves within the full equations of hydrodynamics. First, that our waves are steep and have broad spectrum, which is not actually assumed by the derivation of the nonlinear equation. Second, that in fact many wave systems may be present in the spectrum, and so we may have many peak spectrum, and all this results that the problem how to specify k0 or omega naught, it is not absolutely a priori understood. And it is very important because if you write down this Benjamin Fair index, nonlinearity over dispersion, then in the end it will be proportional to k0 squared. So if we are wrong, if we choose if we didn't choose, maybe if we didn't make choice of k0 properly, then we will be absolutely wrong with the amplitude of the envelope soliton, or we can even miss this envelope soliton in our records. So then waves are not sinusoidal, and as a result it is not not clear how to actually construct the envelope from our very asymmetric waves. And next that full equations of hydrodynamics as well as higher order nonlinear Schrödinger equation approximations to them are not integrable. Therefore, we can pretend only for very rough description by means of the nonlinear Schrödinger equation. And finally, if we try to describe transverse dimension, then we will come to the 2+1 NLS equation, which is not integrable and doesn't have stable Soliton solutions. So therefore, it is absolutely not obvious that we will be successful in application of this theory to the realistic waves. But we can only hope that locally the wave spectrum will be relatively narrow and we will be able to apply the nonlinear Schrödinger equation and its solution for some short, maybe relatively period of time. So we were just, cons, and there are some pros why our expectations may be successful. That first, just, this is what I said. For many years it was assumed that the wave, with the nonlinear Schrödinger equation is able to describe solutions when the steepness is about 0.1 or even smaller. But in the recent time, there are many actually already simulations, numerical and experimental, which show that even very steep envelope solitons can be produced in reality. Therefore, we do really have hope that our approach will work out. So, therefore, it was just preliminary what we wanted to do and why, and now this is what we actually do. We develop what we call windowed inverse scattering transform. So this is our time or space series. We take pieces of our records, and then we consider for each piece we write down the associated nonlinear Schrödinger equation, and we solve the numerically the direct scattering problem for decaying boundary conditions. As a result, we obtain a discrete spectrum which should describe the Soliton part of solution if it is inside this piece. If we obtain lambda, so this is each discrete eigenvalue, then it contains information about the Soliton amplitude, about Soliton velocity. Since we use the sliding window, we are able to find location of the Soliton, and the only point which is not understood, which we do not evaluate, it is phase, complex phase of this solution. So, yeah. And so this is, and we apply this approach to this particular simulation 295, which showed us generation of a huge group of unknowns of agenesis. So this is how we apply our procedure. There are, generally speaking, 3 stages or 3 steps. First, as I said, we apply this window transform. Therefore, as a result, we have a series estimates for amplitudes of solitons which are hidden here. So they are given by red circles. And this is rough and fast first approximation, first solution of this direct scattering problem. Second, we find the situation where the amplitudes of solitons, they form arcs. It means that there are indeed solitons are hidden here, and it is located somewhere here. Therefore, we apply a special procedure to draw curves like arcs through these points, like is shown here by blue line. We are interested only in intense solitons. Therefore, so we just don't, we disregard solitons with very small amplitudes. We take the largest. And finally, at the third stage, we solve once again the direct scattering problem more accurately at a greater window to estimate the amplitude and velocity of the soliton with a high accuracy. So the amplitude is shown by star, location is shown by star, and parameters, amplitude and velocity are given by numbers. So, and we apply it to each time series. And what is benefit of this procedure, that it is absolutely automated. I do not do not give any extra information, just give it a time series or space series and wait for the result. And there are three examples just how it works. These are two figures from the previous slide, first step and second and third step. This was at 11 peak periods from the beginning of the simulation, and this is at large later stage. First phase when the wave has very deep trough, and next situation when it has opposite very high trough. Nevertheless, at each instant of time, the parameters of this soliton, which is hidden here, amplitude and velocity, you can see already that they are estimated with as very close numbers. And we apply it at each time step, and the result we plot the functions. For example, this is by red amplitude of the envelope soliton as function of time. This is the velocity, not velocity. Yeah, this is velocity of the amplitude as function of time, and also about wave number of this associated soliton. First, that the amplitude and velocity, they are very stable during all this simulation run, and it is more than 200 periods of waves. So this is quite a long situation. It is not integrable case. Solitons are very steep. They consist of steep waves, and they interact with other waves, but nevertheless, they have very stable parameter of amplitude. So it means that our procedure works first, and that envelope solitons, or they are similar to them structures, indeed survive or persist in this particular simulation. So this is, I will skip. And finally, the locations of our, given by blue symbols, locations of our maximum soliton, it well agrees the location of the group, which we see by I. So So just in some sense, unfortunately, we cannot just so we do not see clear relation between the maximum of waves, which are given by black and green, and by the amplitude of the envelope soliton. You can see that at different stages, the amplitude of the envelope soliton may be comparable with maximum of waves. At some later stage, the waves may be much higher than the envelope soliton, so it doesn't give us the direct solution how to estimate the maximum wave amplitude, at least at this given instant of time. But we also see at the same time that the most of highest waves appear on top of this envelope soliton. Here you can see by blue local maximum of waves which we observe in numerical simulation, and by red circle the location of a soliton. You can see that they are actually coincide. So therefore we can say that hydrodynamic envelope soliton may be considered as a source of extreme waves. And finally, it's a very recent result, still not published, that there is a great issue, as I said, that if you try to take into account with transverse dynamics in transverse dimension, then even in the first order approximation, the nonlinear Schrödinger equation, it doesn't have stable soliton solutions. Therefore, the problem is how do these solitary-like wave groups behave when we take into account this transverse dimension. What we did, we simulate several cases where we produced the initial conditions for a three-dimensional simulation in such a way that along this longitudinal cut, it is exactly the same initial condition as for simulation 295, but the other waves in this transverse direction, they are actually random, and they satisfy this directional distribution for waves. For example, this is a case with 12 degrees of spread of wave directions. Then we simulate this initial condition. At each time step, we make several longitudinal cuts, and as a result, we have, for example, here 7 space series at each instant of time, and for each this cut, we apply windowed inverse scattering with analysis, and we do the same job as before, and this is the result. So there are two cases are shown here, so-called long-crested with small directional spread and short-crested with large directional spread. There are some examples how these surfaces look like. And what is shown here, the amplitudes of solitons which were found using this procedure. This is time over period, and this is the transverse coordinate. What you can see that for long-crested waves, we do observe some structure similar to envelope soliton, which slowly decay in amplitude. There are some estimations that it lives for at least 50 wave periods, and it has width about 5 wavelengths in the transverse dimension. And the situation is very different for short-crested waves. There are instances of time and locations where wave groups are actually recognized as envelope solitons, but they lose their amplitude just very quickly. So this is not the case. I mean, in these situations, in short-crested waves, envelope solitons do not survive. There are two principally different conditions. This is a set of conclusions. So first, that long-lived soliton-like nonlinear wave groups do exist in the primitive equations of hydrodynamics. So we will call them hydrodynamic envelope solitons because they actually receive the imprint from the strong nonlinearity of the system. So they may be short and steep. They are described in the first approximation by the nonlinear equation envelope solitons. And inherit some key features. I didn't talk about them today, but this is true. So this procedure, windowed inverse scattering technique, seems to be able to reveal soliton-like groups and their parameters such as amplitude, velocity, and location. And as a result, it may be applied as a source of short-term deterministic forecasting of dangerous waves in real sea. And of course, this procedure can be applied in other problems, physical, for example, in nonlinear optics. So this is all, and just after all, this is my invitation. We are organizing a school on nonlinear waves in Nizhny Novgorod, traditional school. So the registration is open, and therefore I welcome all people, especially students. So thank you. I'm ready for questions.
First of all, is it correct that your conclusion is rather optimistic, that if you use framed inverse spectral transform, this approximation is really applicable to ocean waves? Sorry.
Yeah, this is what I want to say.
For me, it's a very good news.
Yeah.
And second, maybe I was asked the question, maybe you know the answer. What's the typical lifetime of rock waves in the ocean?
It's more complicated question because it depends on how you formulate this lifetime. If you are considering if you are staying in one particular point, then all waves they run from this location with high velocity. Therefore, any wave lives for maybe one or a couple wave periods, say 10 seconds or a little bit more. But if you follow the evolution of wave, I say that they live much longer than it is expected and when it is used to think. Because in my simulations, they could live for, at least 50 periods. It means that it is 10 minutes or longer. And so, and then it gives you possibility to forecast if you know that it is for long.
Any other questions? Comments? Okay, I have one. So, one academician told me a story that Soviet Navy people were interested in these rock waves. So.
А можно вопрос? А Петр Георгиевич не будет, что ли, выступать?
Завтра. Когда он будет?
Завтра?
Первым?
Excuse me.
Он будет завтра вместо Погребкова. Так, sorry.
Sorry, just
I see.
About applications in
curiosity question. So apparently, according, I don't know, maybe it's a legend, maybe just a fairy tale. So Soviet Navy was interested in using rogue waves against American aircraft carrier strike groups.
So I just you see, when I gave this talk in front of people who are more or less related to military, it was their first question, how we can apply it. And my answer will be, we will never be able to apply it just because I don't want. At least because. Thank you.
Okay, the next speaker is Professor Brashkin.
Что-то я подумал, выступлю-ка я на русском. Я думаю, так будет правильнее, интересней и больше расскажу. И, соответственно, для людей, владеющих английским, у меня презентация очень с подробными пояснениями. Значит, мы с Ефимом Наумовичем Переновским представляем доклад «Инварианты Каши и точное решение нелинейных уравнений гидродинамики». Ну, мы готовились к данной конференции как в школе плюс конференция, поэтому наше выступление будет содержать как моменты образовательного характера, но они очень интересные, так и моменты. Да, мы как раз рассчитывали, что аудитория до 35 лет здесь будет присутствовать в достаточной степени, но и, конечно, оригинальные моменты в полной степени. Значит, план презентации. Я начну с подробного рассказа, что такое инварианты Каши, как они возникают в гидродинамике. И это непосредственно связано с Лагранжевым описанием жидкости. Мало кто из гидродинамиков пользуется этим описанием, но оно очень красивое, интересное и дает в конечном итоге некоторые очень красивые результаты, непосредственно связанные с точными решениями уравнений гидродинамики. Это вот как раз в пользу названия данной конференции, которая связана с интегрируемыми системами. Дальше, пожалуйста. Итак, как известно, в гидродинамике существует два подхода к описанию движения жидкости. Один подход носит название по имени Леонардо Эйлера, второй подход называется Лагранжевым. Вот они изображены на портретах, соответственно, слева Эйлер, справа Лагранж. Два классика гидродинамики. Дальше, пожалуйста. Ну, что такое Эйлеров подход? Коротко, да? Это мы будем рассматривать в данном случае движение однородной несжимаемой жидкости, идеальной, вязкости нету. Значит, два уравнения. Уравнение несжимаемости, дивергенции скорости равна нулю. Скорость в данном случае это скорость в данной точке x, y, z. F внешняя сила. Вот второе уравнение это уравнение движения. Оно носит название уравнения Эйлера. Слева ускорение, да, там видите нелинейность стоит v на обловые. Справа это действующие силы. Значит, сила градиента давления и F это внешняя сила. Вот подход Эйлера. Значит, это рассматривается поле скорости в данной точке x, y, z. Дальше, пожалуйста. Теперь, что же такое Лагранжев подход? Лагранжев подход связан с рассмотрением траектории жидких частиц. То есть, если мы введем координаты жидкой частицы x, y, z и будем считать, что у нас произведена, то есть мы пометили каждую из жидких частиц некими числами a, b, c, то тогда в зависимости x, y, z вот от этих меток частицы и времени, это как раз будут искомые координаты траектории жидкой частицы. Уравнение непрерывности при Лагранжевом подходе выглядит уже более сложным образом. Вот это уравнение 3, это условие сохранения якобиана, да, преобразование от переменных x, y, z к Лагранжевым переменным. Этот якобиан должен иметь постоянное, ну, в смысле, должен не зависеть от времени. Да? Вот. В данном случае, сразу же обращаю внимание, это одна из трудностей Лагранжевого подхода. у нас, если уравнение непрерывности было дивергенция скорости равна нулю линейной, здесь существенно нелинейное уравнение непрерывности. Первая трудность Лагранжевого описания. Теперь уравнение движения. Как получить уравнение движения? Ну, если мы введем вектор R, вектор координат жидкой, радиус-вектор жидкой частицы с координатами x, y, z, да, то легко записать второй закон Ньютона для движения жидкой частицы. Но это только первый шаг, потому что в силе градиента давления дифференцирование происходит по неизвестным функциям x, y, z. Надо избавиться от этих неизвестных функций. Ну, избавиться можно, поднимите еще, пожалуйста, если скалярно умножить, соответственно, на производную вектора r по a, b и c, тогда у нас, соответственно, можно еще дальше тогда, вот так вот. Вот, тогда у нас, соответственно, уже вылезет производные по А, Б, С у градиента давления. И если в координатной форме, вот уравнение 5, 7, это уравнение движения в форме Лагранжа. Значит, смотрите, квадратичная нелинейность остается, да? Справа градиент давления, ну и внешне действующая сила. Да, извините, опечатка. Ну, сразу же должен сказать, что вот эта система уравнений гидродинамики, она, конечно, отпугивает. Почему еще? Потому что, ну, обычно записывают уравнение непрерывности, вот это уравнение Якобиана, для случая, когда лагранжевые координаты совпадают с начальными положениями частиц. И в этом случае тогда уравнение непрерывности в правой части будет стоять единица. Но, смотрите, уравнение непрерывности, там кубическая нелинейность, здесь квадратная нелинейность. И, вообще говоря, проще, казалось бы, схватиться за голову, да, и вообще не заниматься этими уравнениями. Ну вот, однако, мы пойдем чуть дальше, есть все-таки некоторые интересные результаты. Но прежде, вот, а можно оставить? Это я чуть-чуть это. Во. Хочу обратить внимание, это если хотите рассматривать как некую хохму, да, на самом деле и Эйлерово и Лагранжево описание движения жидкости получил Эйлер в 1755 году. И сам Лагранж в своем письме от 1762 года, он признавал это. Вот. Но вот история науки устроена таким причудливым образом, да, что в какой-то момент один способ стали связывать только с Эйлером, а второй только с Лагранжем. Но здесь поспособствовал этому Дирихле, но это отдельная история. Давайте дальше, пожалуйста. Значит, теперь переходим к тому, что же такое инварианты Каше. Ну пусть внешняя сила будет потенциальная. Тогда сразу же мы видим, что у нас правые части становятся градиентными. Дальше, пожалуйста. Если мы используем перекрестное дифференцирование, ну или возьмем операцию ротора в лагранжевых переменных, ну, дальше немножко помудрим. Здесь от 10 от этого, это дифференцирование по С от 9, это от 10 от 9. Просто перекрестное дифференцирование возьмем, это ротор в лагранжевых координатах. То мы получим три закона сохранения. И поднимите, пожалуйста, чуть-чуть. И вот результат Каше. Каше получил, что вот эти выражения, да, они будут не зависеть от времени, это три интеграла. Значит, обращаю внимание, 1815 год, это результат Каше, но он в классическом учебнике Ламба присутствует, но и, насколько мне известно, но это действительно так, больше как-то про эти инварианты Каше, в общем-то, никто, по большому счету, ничего и не говорил, скажем так, да. Вплоть до определенного времени, это определенное время, ну, в данном случае я просто могу сослаться, уже есть исторические статьи, изучающие историю инвариантов Каше, да, вот, где-то мы в середине 90-х годов прошлого века мы немножко знали этими инвариантами Каше заниматься. В частности, вот в Нижегородской, ага, повыше можно? В Нижегородской нашей школе вот мы придумали и название трем этим инвариантам, инварианты каши, оно утвердилось, и вот сейчас я просто знаю, его хорошо используют на Западе, и Евгений Александрович Кузнецов с Захаровым его использует, в общем, она устоялась, ну, правда, уже никто не помнит, кто придумал это все. Значит, ну, а что вот можно в рамках вот этого описания с инвариантами каши сделать интересного, да? Ну, во-первых, можно ввести вектор инвариантов каши. Значит, вектор S, да, но это будет в лагранжевом пространстве. А0, B0, C0 это единичные векторы, лагранжевые координаты. Что тогда, какие свойства можно получить? Ну, в частности, дивергенция, лагранжевая дивергенция вектора инвариантов каши равна нулю. Можно дальше. Вот, теперь дальше. Результат B. Ну вот его как раз и доказал Каши. Если у нас начальные координаты будут совпадать, если координаты лагранжевые А, Б, С будут совпадать с начальными положениями жидких частиц, то инварианты Каши равны начальным завихренностям. Омега x0, омега y0, омега z0. Ну далее, можно указать некие очень красивые формулы, да, которые связывают завихренность омега, да, с компонентами вектора Каши. Здесь G0 это вот как раз якобиан, значение якобиана вот в уравнении непрерывности. То есть, что в данном случае, какая мысль такая вполне разумная возникает? А давайте просто вот этот вектор...
Поясните, пожалуйста, что такое RA, RB, RC?
А я вводил вектор R, это вектор координат траектории жидких частиц, x, y, z, это его компоненты. А RA это, соответственно, производная вектора R по A, там по B и по C. Радиус вектор, координаты траектории жидкой частицы. И возникает совершенно естественная мысль, а давайте введем вот вектор инвариантов Каши как, ну, определенную гидродинамическую величину, как завихренность, да, ну, если хотите, как скорость. Ну и вообще говоря, это инварианты, про которые мало кто говорит. То есть инварианты в гидродинамике это такая хорошая вещь. Давайте посмотрим, как можно пользоваться вот с этой точки зрения этими инвариантами. Более того, вот ту формулировку гидродинамики, которую я вот только что рассказал, можно опять-таки назвать неким оригинальным взглядом на гидродинамику, да? Никакого давления не включается, это просто форма уравнений гидродинамики, да? В форме инвариантов Каши. Вот давайте посмотрим, можно ли с ней как-то интересно поработать. Можно дальше, пожалуйста. Ну вот здесь вот свойство Е упоминал. Если вот говорить о физическом значении инвариантов Каши, это сохранение потока вектора завихренности через бесконечно малые площадки. Ну или что то же самое, сохранение циркуляции. Ну это вот как раз Каши это и показал. Вот переходим ко второй части. Давайте как-то свяжем вот эти вот уравнения в форме Каши с некоторыми примерами интегрируемости этих систем. Можно вот повыше, вот прямо вот. Ага. Вот я начну с примера, который относится к двумерным течениям, вот 2D геометрия. Значит, в этом случае мы полагаем, что координата z равняется c, это константа, и по третьей координате все производные равны нулю. Тогда у нас из уравнения остается только два уравнения 14-15. Вот уравнение непрерывности – это уравнение движения, да? Ну или сохранение завихренности, поскольку это двумерный случай. Значит, два из инвариантов Каши равны нулю. Вот в этом двумерном случае отличен от нуля только третий инвариант Каши, и он пропорционален завихренности по z. Ну, соответственно, с множителем g нулевое. Оказывается, что вот такую систему можно проинтегрировать, найти частное решение этих уравнений, но оно имеет достаточно такой широкий класс семейства решений. Значит, давайте введем комплексные координаты W, x плюс y и комплексную координаты W с чертой, ну и, соответственно, лагранжевые, комплексные координаты, комплексно сопряженные. Тогда смотрите, вот эти уравнения 14-15 в комплексной форме запишутся вот в таком компактном виде, да, это два якобиана, правая часть у них не зависит от времени, и вот, ну это уже достаточно давно, можно повыше. Вот, вместе с Евсеем и Кубовичем, к сожалению, ушедшим уже в этом году, вот, был найден и исследован класс течений, смотрите, очень интересное решение вот для W. Сумма двух слагаемых, да, G и F это аналитические функции, а лямбда и мю это просто константы, то есть две экспоненты с постоянными константами, частотами. Значит, для инварианта Каши вот такое выражение. То есть, смотрите, класс решений зависит от двух произвольных постоянных частот и двух аналитических функций. Что же это за решение? Можно дальше чуть-чуть. Да. Ну, угадали. Угадали, да. Да. Дальше, можно, пожалуйста? Значит, что же это за решение? Ну, вот это выражение для W – это суперпозиция двух вращений. Первое вращение там с модулем функции G и с частотой лямбда, и накладывается второе вращение с модулем функции F и частотой μ. Ну, такие кривые хорошо известны в геометрии, это эпициклоиды и гипоциклоиды. В зависимости от отношения частот к лямбда, да, это будет либо эпициклоиды, либо гипоциклоиды. Но они могут быть разные. В данном случае это вот как раз траектории жидких частиц. Да? Вот. Ну и учитывая, что именно такого рода траектории были у планет в Птолемеевской системе, вот мы назвали эти течения птолемеевскими. Можно дальше, пожалуйста. Ну вот я здесь просто классификация этих течений. Вот, давайте теперь, да, но в том случае, если одна из частот равна нулю, то траектории частиц будут окружности. Вот давайте теперь пойдем дальше. Значит, если какие-то, можно вот сюда, ага. Если какие-то частные случаи этих птолемеевских течений, да, есть. Оказывается, классическая волна Герцнера, ну, те, кто волнами на воде занимался, должны обязательно были слышать. Франц Йозеф Герцнер в 1802 году опубликовал очень простое решение, да, уравнений в форме Лагранжа. Но оно не только простое, оно вообще единственное точное решение для волн на глубокой воде. Вот 1802 год, в этом году исполняется 220 лет этому решению, да, и это, если хотите, первое точное решение нелинейных уравнений в механике. И мы, скажем так, воспитывались на Солитоне, и очень много докладов и на этой конференции были посвящены Солитону. Но Солитон открыт в конце 19 века, а тут, смотрите, тут 1802 год. Что же это за волна? Может, чуть-чуть дальше. Но в этой волне каждая частица вращается по окружности, да, вот, а сам профиль бежит вправо, оставаясь неизменным. Это так называемые торхоидальные волны. То есть частица, находящаяся на ободе колеса, да, катится вдоль образующей, да, и в этом случае она выписывает трахоиду. Вот такие торхоидальные волны открыл Герцнер, и они получаются как частный случай птолемеевских течений. В данном случае вот это вот решение Герцнера, оно еще на профиле волны, да, порождает постоянное давление. То есть это, ну, скажем так, решение вот классической задачи о волнах на воде с постоянным давлением на поверхности. Можно чуть подальше. Ну вот я хочу подчеркнуть, что вот вместе с Ефимом Наумовичем мы совсем недавно, вот буквально в последнее время, вот эта публикация «Успех физических наук», мы показали два интересных результата, вот, которые относятся к волнам Герцнера. Ну, во-первых, эффект модуляционной неустойчивости для волны Герцнера отсутствует, да? Вот. А во-вторых, Вот если мы рассматриваем слабо нелинейную волну Герцнера в квадратичном взгляд, удивительная формула. Волна Стокса, это классическая волна Стокса в квадратичном приближении, повторяю, равняется волна Герцнера плюс Стоксов дрейф. 3 классических течения, да, связаны вот такой формулой. Как-то мы сами были потрясены, что вообще вот нечто такое подобное. В данном случае квадратичная нелинейность, это уже нелинейность вроде, а здесь и аналог вот такого принципа суперпозиции, и как-то все очень интересно отмечено. Я обращаю внимание, Стоксова волна нелинейная, Герцнер волна завихрена, Стоксов дрейф завихренный. Но завихренность волны Герцнера, она уничтожает завихренность Стоксова дрейфа. Вот такая штучка. Значит, можно дальше. Вот в рамках этих птолемейских течений была нарешена куча задачек всяких разных, ну потому что функции G и F можно выбирать по-разному, да, можно, в данном случае, вот табличку это поднимите, пожалуйста, вот, всякие разные случаи, все это точные решения, единственное здесь осциллирующие солитоны, бризеры, волна с обрушением, там волна на фоне, солитон на фоне волны Герцнера, но единственное, решение точное, но давление на свободной поверхности не постоянно. То есть, ну, это можно моделировать как определенное действие ветра, но в данном случае это вот такое свойство этих решений. Можно дальше. Вот я привожу пример. Вот Алексей рассказывал передо мной про волну убийцы. Вот в рамках птолемейских течений вот можно выбрать так функции GF, что смотрите, вот такой пример организовать. Вот внизу показано, как изменяется давление со временем над волной. И вот тогда из волны Герцнера вот абсолютно спокойно начинает расти пучочек, дальше выше, 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 и в конечном итоге через полпериода вырастает волна. Ну вот тот пример, который мы рассмотрели здесь. Амплитуда в максимуме превышает начальную амплитуду однородного фона, ну, в 9 раз. 9 раз, да? Вот, ну, в зависимости вот от этого перепада давлений, да, вот, если сильный перепад, то вот возможны такие штучки. Ну, по крайней мере, вот как интересный пример, да, волны убийцы. Дальше еще один пример в рамках двумерных течений. Сейчас я перейду. У меня есть еще время? Хорошо, отлично. В рамках еще можно выше. Вот если мы выберем вот такой вид птолемейских течений, да, но теперь областью определения будет единичный круг в лагранжевой плоскости. Смотрите, можно описывать вот такие вихревые области. Вот начальная форма шляпы Наполеона, дальше она начинает вращаться, вытягивается и так далее. Вот я опять-таки скажу, что в классической гидродинамике вот в рамках таких задач известно только одно точное решение, так называемый вихрь Киргофа, но оно является частным случаем птолемейских течений. Можно дальше, пожалуйста, по нему. Ну вот это разные просто виды функций f. Еще, пожалуйста. Вот, теперь, а если у нас трехмерные задачи, да, ну и соответственно, но в двумерных задачах я говорил, что инварианты Каши там будут просто пропорциональной завихренности. Приведу вот такой пример. Будем рассматривать краевые волны. Краевые волны, ну что это такое? Есть у нас наклонный берег, причем наклон однородный. Да? Вот здесь изображено пространство лагранжевых переменных. Вот это вот верхняя поверхность, да, ну она горизонтальная поверхность, и наклонное дно. И наклонное дно. Краевая волна бежит вдоль берега, но от берега амплитуда к периферии убывает экспоненциально. Вот оказывается, это уже трехмерная задача, но и здесь можно организовать интересные точные решения, можно повыше. И здесь смотрите, вот если мы запишем уравнение в переменных Лагранжа, ну здесь просто сила тяжести, у нас там так выбраны были оси, что имеет две компоненты, и вдоль наклонного берега, и ну да, и перпендикулярно ему. Но здесь, если мы опять-таки перекрестное дифференцирование сделаем, пожалуйста, мы опять приходим к той же самой системе. И вот в рамках вот этой задачи, Мы теперь должны что? Мы должны удовлетворить условия непротекания на дне. Условия, ну, в данном случае не будем требовать постоянства давления, а посмотрим, какое оно будет получаться. Вот. Потребуем только, чтобы возмущение на бесконечности, когда мы от берега перпендикулярно уходим, затухали. Можно тогда это? Тогда смотрите, если мы будем считать, что движение происходит в плоскости, параллельной плоскости дна, вот мы z опять такой же выбираем, некоторые функции от c. То есть у нас вот вдоль этого наклонного берега вот все движения вот в этих плоскостях лежат, да? Вот. Тогда у нас уравнения упростятся, да, это мы первое предположение сделаем, и введем новую координату q, b минус c. И мы тогда просто переходим к системе двумерной гидродинамики, которую мы уже исследовали применительно к птоломейским течениям. В данном случае q, вот в данном случае, оно будет иметь смысл b минус c. И мы можем точно так же вот эту птолемеевскую всю динамику применить вот для этих краевых волн. Можно тут поднять тогда повыше. Ага, еще. Ну вот, это вот я все записываю, еще можно, тут уже. Единственное, вот в общем случае давление будет непостоянно. Но какой у нас будет в данном случае инвариант Каши? Инвариант Каши будет вот такого вида, уже зависит от функции g его f. Вот оказывается, что это решение, которое мы получаем повыше, можно? Оно обобщает то решение, которое ранее уже получили, но получил его Константин, да, мы называем его Герцнер-Константин, решение Герцнер-Константина. Вот, отличие от волны Герцнера, то, что здесь теперь стоит не координата b, а b минус c, да, и другая частота. Там у нас ЖК было, ЖК синус альфа. Вот. Но поскольку у нас функции gf произвольные, мы теперь можем выбирать эти функции произвольными, соответственно, у нас это уже трехмерная задача, да, она у нас интегрируема, можно поднять повыше. Вот я выбрал там частые случаи. Вот смотрите, это я рисую ту предельную волну, которая заплескивается на берег. Вот это на длине волны. Вот на берег, на наклонный, натекают вот такие вот нестационарные колебания. Чем интересно это решение? Дело в том, что на берегу, вдоль наклонных берегов наблюдают такие интересные образования, они называются beach caps. Это береговые шапки, то есть наносы песка. И в рамках гидродинамики мы не получали нелинейных волновых решений так, чтобы они были в виде стоячей волны. А здесь это фактически стоячая волна, да, но она не стационарная, то один заплеск, то другой происходит. Но если посмотреть интегрально картину, то они как раз могут, вот серединка, она не поднимается до определенного уровня, а здесь происходят заплески. То есть вот такие вот шапки, да, вот эта волна как раз на берегу может и образовывать. Идем дальше. Просто очень коротко, буквально пунктиром. Вот ту же самую идеологию можно сделать для волн на вращающейся планете в данном случае. Можно повыше. Вот если мы теперь будем рассматривать, допустим, движение жидкости на вращающейся Земле, значит, что мы должны добавить? У нас будет сила Кориолиса, будет центробежная сила, это внешняя сила. Вот сила Кориолиса, она не потенциальная. Но оказывается, для силы Кориолиса можно строить выражение для инвариантов Каши. Можно повыше чуть-чуть. Вот в частности я написал вблизи экватора. Вблизи экватора, в приближении бета-плоскости, у нас вот такие вот выражения 38, такие выражения для инвариантов Каши. Ну, почему я именно около экватора написал это выражение? Можно повыше. Потому что существует точное решение, его нашел. Вот я уже упоминал, это профессор из Вены, Адриан Константин. Он нашел точное решение. И опять-таки, смотрите, оно очень близко к тому, который нашел Герцнер, да? Но в данном случае уже здесь некая произвольная функция h от b. Вот. Но что эта волна описывает? Волна бежит на восток вдоль экватора, но теперь у нее, из-за того, что есть бета-эффект, амплитуда спадает, ну, в обе стороны там от экватора, в обе стороны от экватора. Вот. А внешнее уравнение очень похоже на уравнение на решение Герцнера. И последнее из оригинального можно поднять. Вот оказывается, что схему гидродинамики с инвариантами Каши, Сатирис, можно вас попросить? Ага. Можно. Да, вот здесь еще это решение чем интересно. Смотрите, мы сравним вектор инвариантов Каши с вектором завихренности. И вот в данном случае очень интересно. Если в двумерном случае вектор инвариантов Каши был пропорционален завихренности, там только c3 было отлично от нуля, то смотрите, вот здесь вот инварианты Каши, они не зависят от времени, да, они есть инварианты. А завихренность, вообще говоря, только вот эта вторая компонента не зависит от времени, остальные от времени зависят. То есть в данном случае вот мы нашли характеристику, которая является дополнительной до характеристики вихревых потоков. И самое последнее. Оказывается, что вот эту вот идеологию с инвариантами Каши можно проводить и для уравнения Навье-Стокса, и для учета движения вязкой жидкости. Но вообще говоря, это уже сложность неимоверная в том смысле, что какие-то простые течения вот здесь исследовать можно. Уже, может быть, даже известные точные решения. Вот я покажу чуть далее. Но смотрите, производные по времени инварианты Каши, ротор по лагранжевым переменным – это уравнение непрерывности. G0 – это вот тот наш якобиан, да? G – это метрический тензор, вот он записан. Он состоит из произведения вот матрицы Якоби транспонирована на саму матрицу, да? Вот. Далее идет, ну опять ротор по лагранжевым переменным и та же самая конструкция, но уже вот с вектором инвариантов Каши. Ну, сюда я вообще, если кто-то полезет в эти уравнения, ну это будет супергерой. Но если идти обратным путем, брать известные точные решения, которые можно записать в лагранжевых переменных, то получаются довольно-таки интересные штуки. Вот я, в частности, для течения QE написал, да? Вот здесь вот отличен третий инвариант, да? И он как раз связан с профилем сдвига течения. Можно дальше. Ну или течение Пуазеля в круглой трубе. Можно дальше. Гагин, Пуазеля. Вот. Здесь немножко посложнее, вот. Но в данном случае сама кинематика течения, она исключительно проста. Но я могу сказать, что для всех точных решений, вот, которые удается записать в лагранжевых переменных, ну вот это было сделано, я уже не стал это приводить. Вот. То есть я перехожу к заключению. А заключение такое, что вообще говоря, инварианты Каши есть такая забытая в значительной степени категория, которая, ну, с одной стороны, дает достаточно красивую математику, а с другой стороны, вообще говоря, может где-то пригодиться и в дальнейшем. И в этом смысле вот цель нашего выступления была познакомить вот с этим гидродинамическим объектом. Ну и, может быть, как-то разрекламировать его для будущих каких-то исследований. Спасибо.
Где подробный текст у вас на этот счет? Имеется?
У нас вышла монография с Якубовичем. Называется «Вихревая динамика в лагранжевом описании». 2006 год. Там много из этого есть, но не все.
А вот ваша статья с Ефим Наумовичем уже вышла, да?
Да, это УФН, это 19-й и вот в этом году. Да, пятый номер. Майский.
Есть ли еще вопросы или комментарии?
Спасибо. Меня это интересует давление на поверхности. Для волны Герцнера оно постоянное?
Да.
Для однородной?
Да.
То есть оно становится непостоянным, когда волна Герцнера становится модулированной, то, что вы показывали вот эти.
Да, да.
То есть вот это вот.
Но я опять-таки могу сказать, у Герцнера, ну это хотите недостаток, хотите свойства, но Это вот с точки зрения Лагранжевого описания, это самый яркий признак. Нет дрейфового течения, то есть траектории частиц окружности. Как мы только добавляем дрейф, так...
А еще такой может быть, момент. То есть было сказано, что модуляционной неустойчивости нет, но вот было представлено решение типа вот FreeWave, которое очень похоже на модуляционную неустойчивость. Вот как одно с другим связано? Или не связано?
Ну, во-первых, это нелинейная волна. Там же мы смотрим методом многомасштабных разложений квадратичные линейные решения.
То есть она может быть неустойчива в более высокой степени нелинейности?
Нет, более того, мы же вот для FreeWave там тоже неоднородное давление на поверхности.
Это я понимаю.
Вот. А здесь, когда мы считали нелинейный Шреддинг, мы сдавали давление постоянное на поверхности.
То есть возможно, что оно просто давит?
Да. Так, нет, физический механизм что давит, да.
Понятно, спасибо.
Еще вопросы, комментарии? Ну, давайте поблагодарим докладчика еще раз.
Спасибо.
Следующий докладчик — профессор Зольникова из Москвы.
Не все. Как она действует? Это вперед? Это указка. Ага. Угу. Ну, надеюсь. Итак, прежде всего, что касается языка, я буду следовать... Работает? Я буду следовать традициям нашей конференции. Если никого онлайн из иностранных участников нет, то я буду продолжать традицию предыдущего докладчика, то есть говорить на русском. Итак, прежде всего я хочу, конечно, поблагодарить организаторов за то, что пригласили сюда, на такую прекрасную конференцию, в такой прекрасный город, для того, чтобы я смогла представить здесь деятельность группы профессора Николая Сергеевича Ерохина из Института космических исследований и нашего болгарского соавтора Румена Шкеова, с которым мы взаимодействуем довольно долго и довольно плотно. Ой. Не то, не работает. У меня техника обычно не работает. Так. Значит, дальше. Наша работа посвящена исследованию резонансного взаимодействия волна-частица в космической плазме. Можно следующий слайд? Значит, это и теоретическое, и численное исследование резонансного взаимодействия, которое основано на исследовании уравнения, дифференциального уравнения второго порядка. Это уравнение является нелинейным, нестационарным и описывает поведение фазы волны на траектории захваченной частицы. Этот подход для исследования захваченных частиц довольно удобный, потому что позволяет наглядно исследовать динамику захвата, поведение частицы внутри потенциальной ямы и процесс вылета из нее. Нет, пока еще. Ага. Так, значит, известно, что космические лучи были открыты более 100 лет назад, но до сих пор единого механизма ускорения частиц как бы не существует. И энергии частиц, которые прилетают к нам на Землю из космоса, как показывают последние измерения, они достигают очень больших величин, порядка 10 в 20 степени электрон-вольт. И мы будем исследовать так называемый серфотронный механизм ускорения заряженных частиц. Почему такое название серфотронный, я объясню немножечко позже. Волновым пакетом с лоренцовской огибающей. И основная цель нашей работы посмотреть, насколько этот механизм эффективен, насколько он может разогнать частицу с довольно низких энергий до момента ее вылета. Так, теперь можно дальше. Взаимодействие волна частицы в применении к ускорению частиц было начато в работах, в серии работ Сагдеева, но наиболее фундаментальной работой, которая распространила эти идеи на релятивистский случай, является работа Кацулиуса Даусона о неограниченном ускорении электрона в лазерном пучке. Они ввели термин unlimited, неограниченный, но этот термин не совсем корректный, потому что, естественно, резонанс, условия резонанса далеко не всегда могут быть выполнены. Когда-то они кончаются из-за того, что параметры среды, параметры частицы и так далее у нас нарушат этот резонанс. Итак, в космосе. Причем мы рассматриваем холодную плазму. Можно следующий слайд? Сейчас я значит, и вот здесь вот представлена начальная часть работ, с чего начиналась работа под руководством Николая Сергеевича Ерохина, но это вот самое начальное, там дальше их будет больше. Так, следующий слайд. Итак, вот теперь немножечко о нашей модели и основной теории. Значит, что мы имеем? Мы имеем холодную плазму плоскости по плотности n нулевое, бесстолкновительная. И в этой плазме существует внешнее слабое магнитное поле, направленное вертикально вверх. То есть О и Z мы изначально возьмем параллельно магнитному полю H0. Что делают частицы, находясь в таком магнитном поле? Ну, это известно со школы. Если скорость у них в плоскости x, y, то частица совершает вращение вокруг магнитных силовых линий с частотой, с гирочастотой омега-h. Если у нас имеется z-компонента, то движение начинает принимать спиралевидный характер. Окей, теперь появляется электромагнитная волна. Для начала монохроматическая, с частотой омега. Что происходит? Если фазовая скорость этой волны далека от скорости, волна распространяется в направлении x. Значит, если скорость частицы и скорости волны довольно разные, то не происходит ровным счетом ничего. Они встречаются и разлетаются. Если же скорость частицы приблизительно очень близка фазовой скорости волны, вот тогда начинается интересный момент, что частицы оказываются захвачены в потенциальную яму монохроматической волны и начинает двигаться вместе с этой волной. И начинает, что происходит? Частица двигается вместе с волной, начинает набирать энергию, магнитное поле может ее закручивать, и ускорение может происходить параллельно волновому фронту частицы. И при этом частица будет набирать энергию. Однако, очень часто случается так, что у волн в плазме фазовая скорость больше, чем скорость ц, а частицы не умеют летать со скоростью больше, чем скорость света. Поэтому нам надо найти такую волну, которая бы имела еще и фазовую скорость меньше скорости света. Оказывается, нам повезло, такие волны есть. Это волны биполяризации, у которых компоненты X, Y и H, Z, и частоты близки к верхнему гибридному резонансу. Так, следующий. Можно назад еще. Значит, здесь пси – это фаза волны, хи – это отношение компонент тензора диэлектрической проницаемости. Значит, параметр хи, он отвечает за непотенциальную часть электрического поля. Так, ну, собственно, из интересных моментов здесь, да, ну, омега-ПЕ – это известно плазменная лингвировская частота. И вот еще два параметра, два важных, они введены были в книге Гинзбурга. Параметр У – отношение гирочастоты к частоте волны, и параметр В – отношение лингвировской частоты электронной к частоте волны, квадрат этого отношения. Это просто для удобства дальнейшего изложения. Так, следующий. Значит, можно записать условия релятивистские уравнения движения для компонента импульса. Вот они. И удобно ввести безразмерные переменные тау, кси, бета – это отношение векция скорость частицы, и безразмерную амплитуду сигма. Так. Далее. KOZLOV и Даусон в своей знаменитой статье показали, что ускорение частиц возможно, если выполнено условие на амплитуду волны. То есть амплитуда волны должна быть больше некоторого критического значения, равного U на гамма-P, где гамма-P – это релятивистский фактор волны. Так, следующий слайд. Значит, можно записать выражение для x-компоненты скорости электрона, и тогда наше уравнение для импульсов примут вот такой вид. Так, да, здесь видно, что у нас по z ничего нет, что импульс по оси z у нас постоянно, то есть возникает уже первый интеграл движения. Так, дальше. Дальше можно получить уравнение для релятивистского фактора электрона. И, используя предыдущее уравнение и это, можно получить второй интеграл движения. Итого мы имеем в нашей задаче два интеграла движения. Значит, опять-таки переписываем в следующем виде. Значит, параметр гамма, выражение для y-компонента волны. Дальше. И получаем в итоге вот это нелинейное уравнение для фазы волны на траектории заряженной частицы. Уравнение электрона. С начальными условиями пси от нуля равняется пси 0, и производная равняется это отстройка от резонанса. Но мы тоже будем пока ее будем брать 0. Вот, казалось бы, у нас вот имеется вот такое уравнение. Следующий слайд, значит, он иллюстрирует два случая. В случае слабой релятивистскости, вот видно, как электрон сначала двигается в направлении X, и магнитное поле его закручивает, и он начинает двигаться параллельно волновому фронту. Ну и процесс ускорения, процесс набора энергии будет происходить параллельно волновому фронту. Дальше. Следующий слайд это для ультрарелятивистского случая. В этом случае электрон у нас как бы прилипает к задней стенке волны, и волна его толкает. И происходит набор энергии электрона. То есть видно, что поведение электрона, оно очень напоминает поведение серфера на обычных океанских волнах. Так, дальше. Значит, вот хотя то уравнение второго порядка, оно с виду кажется не очень сложным, не очень страшным, но, однако, задача не является такой тривиальной ввиду того, что она многопараметрическая. Значит, от очень большого количества параметров зависит, то будет захвачена частица, не будет захвачена частица. Это и скорость частицы, и наличие магнитного поля, и величина магнитного поля, возможно, кривизна магнитного поля, скорости частиц, скорости волны, направление движения, плотность плазмы, возможно, неоднородность плазмы можно учитывать, и так далее, и так далее. Вот для случая монохроматической волны мы в одной из ранних работ просто просчитали для двух параметров, для начальной фазы и для параметра U, с шагом 1/100 по каждому параметру области, при каких значениях, вот в случае только вот этих параметров, остальные вот параметры были фиксированы и взяты, вот как показано вот там, есть захват или нет. И видно, что даже вот в случае вот двух параметров у нас наблюдается довольно сложная структура областей, в которых захват происходит в начальный момент. Здесь еще не учтены области, такие серые зоны, потому что частицы могут совершить какое-то количество ларморовских вращений и потом захватиться. То есть, в принципе, сам процесс, сама задача не является такой уж очень тривиальной. Ну, однако, вот то, что вот я рассказывала, это идеализация. Монохроматических волн в природе, как известно, не существует. Это такой же идеальный объект, как в математике точка или прямая линия. А обычно в природе имеют дело, можно следующий слайд, с волновыми пакетами. То есть у нас имеется некий волновой спектр, волновой пакет с несущей частотой омега-0, в дисперсионном соотношении омега от К0. Мы выбрали лоренцовскую огибающую для данного волнового пакета, ввели безразмерные переменные, параметр L характеризует ширину пакета на половине амплитуды, и безразмерная ширина пакета у нас характеризуется параметром ρ. Значит, она должна быть довольно большой, больше, чем 10 в четвертой степени. Мы в своих расчетах брали, по-моему, 70 тысяч, 7 на 10 в четвертой. Вот. И мы начальное взаимодействие, значит, у нас пакет распространяется с групповой скоростью, и внутри несущий имеет свои, значит, локальные потенциальные ямы. Мы брали начальное значение потенциальной ямки, которая находится вблизи центра пакета. Так, можно дальше. Значит, в этом случае наше уравнение сводится к вот такому вот виду. Так, на вид оно, конечно, ничего страшного не представляет. значит, параметр выписан. И следующий слайд. Ну, в полном виде вот так вот оно выглядит. И вот это вот уравнение мы исследовали. Да, это уравнение, опять-таки, допускает аналитическую аппроксимацию для релятивистского фактора. Вот она имеет линейный вид. Вот такой, где, значит, гамма от нуля – это релятивистский фактор частицы в момент времени 0. Так, дальше. Дальше, значит, производились, собственно, расчеты для оценки эффективности. Так как процесс ускорения у нас довольно длительный, мы считали до 80 тысяч, здесь я привожу только один наиболее, ну даже не наиболее характерный вариант. Мы делали разные варианты, но чем вот этот вариант замечательно, что в этом варианте у нас захватились практически все частицы. При разных вариантах, вот, так же, как с монохроматической волной, были случаи, для которых существовал диапазон фаз или отдельные фазы, для которых условия резонанса не было выполнено не только сразу, но и вообще за время длительного счета. Но вот при таких параметрах, как мы дальше увидим, значит, мы исследовали диапазон начальных фаз от минус π до π, ну, грубо говоря, от минус 3,1 до 3,1 с шагом 1. И смотрели, какую энергию приобретает частица с такими параметрами, то есть с начальной энергией. Начальная энергия, релятивистский фактор для них составляет 1,536 гамма от нуля, а начальная энергия составляет 0,785 мегаэлектрон-вольт. Так, можно дальше. Ну, вот на этом слайде представлена как раз вот динамика поведения частицы, собственно, решение зависимости фазы на траектории частицы. Мы видим довольно мелкие колебания. Значит, этот случай, когда дельта-π0 отстройка вот от начала середины пакета величина равняется 2, и при вылете эта частица достигла 4 гигаэлектрон-вольт. Вот мы видим, сначала идут колебания, а потом фаза начинает расти. Это означает, что частица наша вылетела из потенциальной ямы. То есть все очень наглядно. Можно следующий слайд. Вот на следующем слайде более подробно показана начальная стадия. Вот идет, частица попала в волну и в яме совершает колебания вблизи дна потенциальной ямы. Вот, вот начальная стадия. Так, дальше. Вот, значит, опять на этой картинке. Вот эту картинку мы видели уже. Вот точкой показана точка, где мы считали, что частица уже вылетела из ямы, где энергия все пошла, фаза пошла уже в рост. А здесь представлена фазовая плоскость, фазовая траектория для движения этой частицы. Значит, как ведет себя эта частица? Сначала, значит, стрелочки не нарисовали, частица, движение идет оттуда. Частица захватывается, совершает некоторое небольшое количество в верхней части потенциальной ямы, потом довольно быстро скатывается на дно потенциальной ямы, и потом она медленно выбирается и вылетает оттуда. Значит, это все для наиболее характерного случая, наиболее общего такого случая. Это начальная фаза равняется 2,0. Так, следующий слайд. Да. Значит, во время наших исследований мы обнаружили, вот эти фазовые траектории мы называем траекторией серфотронного резонанса. И мы обнаружили два типа таких фазовых траекторий. Одна траектория, когда частица захватывается и мигом сваливается на дно потенциальной ямы, долго-долго там вращается, находится, и потом медленно выбирается. А другой тип фазовых траекторий, когда у нас частица захватывается и аккуратно, медленно спускается, совершает какое-то количество движений вблизи дна, и потом также медленно выбирается из потенциальной ямы. Значит, мы назвали эту траекторию типа 1, это по форме кривой тип W. Так, дальше. Вот так. Теперь переходим, собственно, к эффективности. Значит, здесь представлен график релятивистского фактора. Для фазы, какая тут фаза? Да, вот фаза, отстройка от нуля, начальная фаза 2,0. Да, начальная энергия для всех вариантов у нас одинаковая, 0,785 мегаэлектрон-вольт. И для этого случая у нас энергия вылета составила 4,9 гигаэлектрон-вольт. То есть увеличилась практически на 3 порядка по величине. И здесь для сравнения представлен график нашей аналитической аппроксимации. И в точке вылета значение, которое дает расчет релятивистского фактора наш, 7814, и по аналитической аппроксимации 7816, ну, практически они совпадают. Единственное, что наша аппроксимация пока не может описать момент вылета, но это, опять-таки, довольно-таки сложно. И бывает еще момент, когда у нас частица захватывается не сразу. Тогда у нас, я здесь не привела картинку, но словами скажу, у нас график релятивистского фактора какое-то время болтается в районе начального значения, а затем после захвата идет параллельно вот этому. В этом случае наша аналитическая аппроксимация дает такой же скорость роста, скорость нарастания. Так, следующий. Можно? Так, здесь на этих картинках представлены времена захвата, при которых произошел захват ускорения под красным цветом, и темным цветом представлены времена вылета частицы из потенциальной ямы. Значит, 2,0 это вот как раз здесь отмечено, почему мы выбрали как наиболее характерную 2,0. То есть вот очень много частиц похожее поведение показывают. Значит, что мы видим? Мы видим, что часть частиц у нас захватились сразу, а некоторая часть частиц, они захватываются после того, как совершат какое-то количество гировращений. То есть только тогда будет выполнено условие захвата в резонанс. Ну и вот здесь на этом рисунке представлено время ускорения, то есть разница между временем вылета и временем влета. И видно, что минимальное время ускорения вот в условных единицах 35-138 соответствует релятивистскому фактору 6,290, энергии вылета 3,21 гигаэлектрон-вольт. И максимальное время ускорения 57,690 для начальной фазы 1,3, и энергия вылета 4,12 гигаэлектрон-вольт. Ну и вот здесь параметр отношения энергии вылета к начальной энергии, во сколько энергия вылета больше, чем влета, это в 5244 раза. Следующий можно? Так, здесь у нас зависимость релятивистского фактора, тоже опять-таки от начальных фаз, минимальное значение релятивистского фактора 6,290, максимальное 8,056. Следующий. Здесь у нас энергия вылета. Опять-таки максимальная энергия вылета у нас 4,12 гигаэлектрон-вольт, минимальная энергия 3,21 гигаэлектрон-вольт, соответствующая фазе минус 1,9. Так, и следующий слайд. Ну и отношение, во сколько раз энергия вылета больше, чем энергия влета. Тоже похожие графики, тоже и четырехзначные цифры. То есть можно... Ой. То есть, значит, что мы имеем? Значит, происследовав ускорение частиц пакетом электромагнитных волн с Ленгбергской огибающей и взяв начальную энергию 1,536 мегаэлектрон-вольт и начальную позицию в центре пакета и проведя вычисления для различных начальных фаз от минус π до плюс π шага 0,1, мы получили, что вероятность захвата в резонанс близка к 100%. Но это опять-таки это для данного конкретного выбора параметров. Далеко не при каждом выборе параметров у нас такая вероятность. Но здесь 74% у нас сразу захватываются, остальные 26% после какого-то количества гировращений. Ну и начальная энергия у нас увеличивается более чем на 3 порядка по величине. Вот такие основные выводы. Все. Спасибо за внимание.
Вопросы к докладчику?
Там, когда есть пакет, как это становится? Групповая скорость и фазовая? Что больше?
Групповая скорость не очень большая. Фазовая выше, конечно.
Есть ли еще вопросы? Комментарии? Ну, давайте поблагодарим докладчика и кофе номер...
Я удалял файлы.
The next speaker is Dmitry Belonoshko from Yaroslavl University. He will speak on the critical velocity of Kelvin-Helmholtz instability realization. Slides.
Я прошу прощения, я буду по-русски говорить. Мое сообщение называется о критической скорости неустойчивости, реализации неустойчивости Кельвина-Гельмгольца. И с названия может быть не совсем понятно, о чем идет речь, поэтому короткое вступление. В моем сообщении речь идет о двух явлениях. Одно явление – дрейф Стокса. Вы можете видеть на слайде ссылки на статьи, в которых начало описываться это явление, и публикации некоторых последних лет, до сих пор оно исследуется. Явление состоит в следующем. Если по поверхности жидкости распространяется периодическая волна, в данном случае на рисунке она вправо совершается, если проследить за отдельной жидкой частичкой, которая сидит на поверхности жидкости, то она совершает не круговые движения, как в большинстве книжек пишут, а движения по незамкнутым петелькам с каждым новым периодом, возвращаясь не в предыдущее положение, а немножко смещенные относительно него в направлении распространения волны. Этот сдвиг в сумме складывается в дрейфовые движения, которые называются дрейф Стокса. Если посчитать скорость дрейфа, то получается формула 1. Этот дрейф, он пропорционален квадрату амплитуды, экспоненциально убывает с глубиной по амплитуде, и он явление второго порядка малости. Для того, чтобы его обнаружить, нужно в гидродинамике идти не просто в теорию линейных волн, а как-то зацепиться за теорию волн немножко нелинейных, хотя бы во втором приближении по амплитуде волны. Это первое явление, на котором основан мой доклад. Второе явление тоже хорошо известно, наверное, даже лучше, чем дрейф Стокса, неустойчивость Кельвина-Гельмгольца. Неустойчивость Кельвина-Гельмгольца – это неустойчивость малых возмущений на границе раздела двух жидких сред. Я рассматриваю в постановке эту неустойчивость, когда нижняя среда более плотная, чем верхняя, на границе раздела есть поверхностное натяжение. И вот если верхняя среда двигается относительно нижней в среднем со скоростью u0, то существуют условия, когда малые возмущения на поверхности начинают расти. Если простым языком, это неустойчивость, которая отвечает за появление ряби на поверхности водоема, над которым дует ветер. Внизу написана формула для порогового значения скорости, выше которой неустойчивые возмущения появляются и действительно реализуется вот эта ситуация с рябью. Здесь стандартное обозначение ρ без штриха – это внизу плотность, ρ со штрихом – это вверху плотность, k – волновое число, гамма – коэффициент поверхностного натяжения. Явление хорошо известное, и вот это явление, оно считается на уровне критической скорости. В линейном приближении по амплитуде волны нужно решить линейную задачу, и чтобы определить критическую скорость, пороговую скорость, выше которой начинается неустойчивость, линейной теории по амплитуде волны достаточно. Мое сообщение о том, что вообще-то неплохо было бы проследить в теории неустойчивости Кельвина-Гельмгольца за тем, как двигаются жидкие частички в нижней среде и в верхней среде, как раз в ситуации, когда верхняя среда двигается над нижней. Ведь поскольку в одной жидкости волны инициируют дрейф второго порядка малости по амплитуде волн, то в системе двух жидкостей с границы раздела тоже должен инициироваться какой-то дрейф. В нижней жидкости его, наверное, тоже можно называть дрейф Стокса. Это наследник того дрейфа Стокса, который классический, про который я рассказывал. А в верхней среде появится дрейфовая добавка к скорости U0, к средней скорости, с которой постоянно движется верхняя среда. На слайде вы можете видеть математическую формулировку задачи. Достаточно просто. Я не ухожу в какие-то вязкие жидкости в этой формулировке. Нижняя жидкость опять более плотная, чем верхняя. Верхняя в среднем двигается со скоростью U0. Уже есть на поверхности какое-то волновое искажение. Еще раз подчеркивание, оно уже есть, оно не возникает там по каким-то причинам. Оно вот может только нарастать в результате неустойчивости или распространяться из-за того, что диссипации нет. И нужно рассчитать потенциал скоростей φ в нижней, верхней жидкости. И, зная этот потенциал, рассчитать дрейфовое движение в нижней жидкости и добавку к дрейфовому движению в верхней жидкости. Здесь вот задача приведена в полной формулировке, то есть никакие нелинейности здесь не отброшены. Как я уже сказал, дрейф – это феномен второго порядка малости по амплитуде волны. И, естественно, нужно задействовать решение второго порядка малости. Эта задача решалась таким образом. Стандартным образом в теории волн малой амплитуды, то есть мы вводим малый параметр, который равен отношению амплитуды волны, амплитуды искажения к его длине. Этот параметр считаем малым, раскладываем все уравнения граничные условия по этому малому параметру и разбиваем задачу на задачу нулевого, первого. Ну и как-то нужно включить задачу второго порядка малости. И вот мы с автором Артемом Мачировым разработали процедуру, которая позволяет, во-первых, успешно эти действия выполнить, а во-вторых, еще перейти от переменных Эйлера к переменным Лагранжа. Дело в том, что вот та формулировка, которая написана, она вам дает потенциал, а из него и скорость, не жидкой частички, а скорости жидкой частички в фиксированной точке пространства. Через эту точку пространства, сменяя друг друга, проходят разные жидкие частички, и поэтому, получив скорость из решения этой задачи, мы не получаем непосредственно скоростей движения жидких частичек и, соответственно, не получаем каких-то дрейфовых компонент. Вот. И мы разработали процедуру, с помощью которой это можно сделать. Это сделали. Вот. И получилось. Ну, дисперсионное уравнение это можно взять, наверное, из любой книжки. Оно с точностью до обозначения то, которое всем известно. Вот. А для траекторий жидких частиц получились вот конкретные выражения. Это выражение 9-10 для нижней жидкости, частички в нижней жидкости, но она вот сидит именно на поверхности. 11-12 это в верхней жидкости, тоже частичка, которая сидит на поверхности. И, как видно, красным выделены компоненты, которые являются непериодическими, это как раз в точности дрейфовые компоненты. И можно проследить, как они себя ведут в зависимости от скорости верхней среды. Именно это и было сделано. Прежде чем как-то подробные расчеты проводить, мы результаты сверили с экспериментом, который нашли в литературе. На слайде вы можете видеть ссылку на статью, где результаты эксперимента. На левом рисунке вот именно экспериментаторы отслеживали траектории жидких частичек на поверхности раздела двух жидкостей. И они привели данные, по которым мы провели свои расчеты. И, в общем, если накладывать, то все как раз очень хорошо совпадает. Мы считаем, что теория, которая построена, она, ну, по крайней мере, при малых длинах волн, она хорошо работает. Проведена сверка с экспериментом. Но эксперимент вот был проведен, только две жидкости просто граничат друг с другом, одна не движется относительно другой. жидкости. Что получается, если движение происходит? Вот на слайде можно видеть основные типы течений, которые получаются в зависимости от значения скорости верхней среды. Ну, естественно, что диапазон скоростей от нуля до бесконечности делится, во-первых, на диапазон от нуля до критической скорости. Пока мы находимся в области меньшей критической скорости, неустойчивость Кельвина и Гельмгольца не наблюдается, волны просто распространяются без затухания, как периодические волны, и все, никакого роста амплитуды нет. И уже в этой области вот такие результаты получаются. Пока, ну, мы, естественно, берем какую-то волну, задаем волновое число или длину волны, какую-то конкретную волну и смотрим, как для нее ситуация развивается. Для конкретизации мы брали длину волны наиболее неустойчивую по отношению к неустойчивости Кельвина и Гельмгольца. И вот что получилось. Пока скорость движения верхней среды меньше фазовой скорости волны, то есть пока поток вверху как бы догоняет гребни волн, получается такая ситуация. Вот смотрите, внизу, как на самой первой картинке, происходит дрейф Стокса за счет петлеобразного движения жидких частичек, вверху этот же дрейф, добавочный к скорости U0, он в ту же сторону направлен, но закручен в другую сторону. Вот таким вот образом. Как только мы достигаем скорости фазовой, частички, сидящие со стороны верхней жидкости на поверхности вот этой волновой, они перестают петлеобразно двигаться, а просто по прямым двигаются. А как только мы переходим в область, где фазовая скорость больше групповой, смотрите, направление петлеобразного движения, оно меняется на противоположное. И вот если жидкие частички, если скорость верхней среды больше, чем фазовая скорость волн обгоняет вот гребни волн, то в верхней среде, смотрите, дрейф добавочный, он противоположен, а движение жидких частичек совершается по петлеобразным траекториям с закручиванием вот в другую сторону по сравнению с предыдущей ситуацией. Вот, может быть, про закручивание это даже излишняя деталь для моего рассказа. Главное, что при достаточно большой скорости добавочный дрейф, который добавляется к скорости U0, он направлен вот в противоположную сторону дрейфу, который внизу жидкости развивается. Если мы переходим в область неустойчивости, перешагиваем порог неустойчивости, то смотрите, в верхней жидкости по разворачивающейся спирали, в нижней жидкости по разворачивающейся спирали частички начинают двигаться в одну сторону, в нижней в другую, и эти дрейфы направлены навстречу друг другу, они все больше и больше стремятся компенсировать в среднем ту скорость, которая вызвала неустойчивость Кельвина и Гельмгольца. Вот само это отличие, оно очень простой вид имеет скорости относительного движения жидких частичек от скорости U0. Зета квадрат – это амплитуда волны на как квадрат. И вывод такой. Классическая неустойчивость Кельвина и Гельмгольца нам говорит о том, что если имеются две среды, одна среда двигается на другой со скоростью U0, линейная теория волн нам дает критическое значение скорости, выше которого развивается неустойчивость Кельвина и Гельмгольца. Учет дрейфовых составляющих в скорости течения нам говорит о том, что на самом деле скорость относительного движения, она несколько меньше той критической, которую дает линейная теория. Это вот такой необычный результат, про который я и хотел рассказать. То есть в классической теории неустойчивости Кельвина и Гельмгольца считается, что вот есть конкретные выражения, а если вот этот небольшую нелинейность учесть, связанную с амплитудой в квадрате, то эту скорость, если смотреть на относительную скорость движения жидкости, верхней относительно нижней, она на небольшую величину, амплитуда в квадрате на волновое число в квадрате, на самом деле меньше. Вот это основной результат. И я на слайде, который у вас сейчас перед глазами, как раз перечислил. Итак, критическая скорость развития неустойчивости Гельмгольца оказывается немножко меньше, чем принято считать. На начальной стадии развития неустойчивости Гельмгольца добавочный дрейф, который индуцируется и в верхней, и в нижней среде, они направлены навстречу друг другу и стремятся уменьшить разность скоростей, отвечающих как раз за относительное движение. И вот внизу написано, это приводит к уменьшению относительной скорости индивидуальных жидких частиц, при которых происходит неустойчивость, и этот эффект развивается по мере нарастания неустойчивости. Спасибо за внимание. Мой доклад закончен.
Спасибо. Я на самом деле переспрошу, наверное, то, о чем вы говорили, просто, может быть, немножко другими словами. Вот смотрите, допустим, у нас вода гладкая, там начинает дуть ветер, ваша поправка, ее фактически нет, нормальная неустойчивость в соответствии с обычным критерием. Начинается рост волн, так? Появляется добавка вот в соответствии с тем, что вы сделали. Она препятствует дальнейшему росту?
Да, препятствует. Да.
То есть это механизм ограничения?
Дополнительно еще к вязкости и к другим механизмам, которые есть. Это дополнительный механизм ограничения роста волн.
То есть это нелинейный механизм ограничения развития неустойчивости?
Да.
Спасибо.
Есть ли еще вопросы к докладчику? Комментарии? Ну, давайте тогда поблагодарим еще раз.
Спасибо.
На сегодня все. Завтра ждем вас по расписанию.